Yeah. Good morning. Look at all these pretty faces. Uh, I guess the crowd's a little bit thinner because we stayed out too late last night, but maybe they'll come on in. We're going to start this morning with CubeSat Sim with Alan Johnson, and we will proceed through. We'll take our break about midway through, and then this goes on till 3 p.m. At which time we'll have the AMSAT annual member meeting. And then we have, of course, the banquet tonight. Again, let me remind you, when we get to the question and answer period, if you have a question, raise your hand. I'll come over and bring a microphone to you because we are live streaming on the internet. Thank you. Uh-oh.
Okay, thanks, Robert. I'm Alan Johnson, KU2Y. I'm AMSAT's Vice President for Educational Relations, and I'm also an Associate Teaching Professor at Villanova University. It's a pleasure to be here this morning, kicking off the second day of the Symposium. So I'm going to introduce the CubeSat Sim, the CubeSat simulator. Who here has heard me give a presentation on the CubeSat Sim? Okay, yeah, most people. Okay, that makes sense. The good news is that we have other CubeSat Sim presentations that you have not heard before. Agustia, who's going to present after me about a workshop that was done using the CubeSat Sim. We have Frederick there in the second row there, who is going to present about CubeSat Sim and SatNox. And then finally Larry. Where's Larry? Larry. Oh, he will be here, I guess. Oh, there's Larry, sorry. Is going to present about his CubeSat Sim builds, actually, because he's built more than one CubeSat Sim. So I'm going to talk a bit about what the CubeSat Sim is, but I'm going to go pretty quickly through that since most of you are familiar. But I'm going to spend most of my time talking about what are some of the new things that my team and I have done this year. And then we're going to end with a live demo, which of course will fail, just telling you that in advance. I'll be demoing a number of different modes. If any of you have an HT with you, you can participate in the demo. So we'll see when we get to that point. So I just want to start by acknowledging the team that works with me on the CubeSat Sim. Without Frederick, Mark, and David, we wouldn't get half of this done. And of course, Frederick is here this week. We met for the first time in person after working together for 4 years, which is kind of crazy. But anyway, so hopefully Mark and David can come to other symposiums in the future too. But thanks to them for all the time that they put into this project. So what is the CubeSat Sim? It's the core of our education program here at AMSAT. Of course, we have AMSAT engineering that builds our spacecraft, our actual satellites that go into space, and you're hearing a lot about that from the engineers. But what we build is fully functional models for the classroom. And that way they're low cost, easy to build, and good for learning, good for STEM outreach. And they're used in university programs, they're used in high schools, the amateur radio community, people demonstrate them at hamfests and the like. And also we're starting to make some inroads with libraries, museums, maker fairs, things like that as well, because they make good demos. So there's the picture of the 1U. I have a 2U that I've built here that we'll be demoing, but it's basically the same thing, just with a bigger frame. But that's what the 1U one looks like. And it's basically the same thing that we send to space, except this one would last about 1 second if you actually send it to space. Right? Given that it's got a plastic frame and it's just running ordinary code on a Raspberry Pi, it would not fare very well in space. But it's designed to be low cost and easy to build, which is not two things. If you're going to send something to space, those aren't your prime requirements. So inside there are 3 custom boards and also a Raspberry Pi 02, which runs the main software. And we also have a Raspberry Pi Pico microcontroller, rechargeable batteries, voltage current sensors, environmental sensors. So it's got a little bit of everything. And it transmits real telemetry on the 70 centimeter band. So if you have your HT with you and you tune to 434.9 megahertz, you can hear it transmitting once we power it up. And for the ground station, we use the same exact software that AMSAT uses for our CubeSats that are in orbit. So whatever you learn with the CubeSat Sim, you can directly apply that to real satellites. You just need a proper antenna and tune in at the right time and the right frequency for that. Okay, so a little bit about the technical details. So the Raspberry Pi 02 is the heart of it. Runs the housekeeping software, which is written in C and Python. And everything about the CubeSat Sim is open source. It's all on GitHub. There are quite a few forks, and quite a few people have done pull requests for it. So we're starting to build a community of developers. But I've written most of the code myself. And it has a Pi camera in it for the imaging modes. And it also has a USB sound card, which we use as a microphone input for doing our command and control. The software still runs on a Pi 0, but it's kind of getting towards the edge of the horsepower that you need. And Pi 02s are cheapish, so that's why we've switched to them. So the main board, it's got the most things on it, and it includes the Raspberry Pi Pico microcontroller, which is a really nice board, very, very inexpensive. The purpose of that is it talks to the payload sensors. So we have a division of software between the housekeeping software and the payload software. And we actually utilize that in that you can add sensors to it and you don't have to modify the main housekeeping software. You just add some code to using, for example, your Arduino IDE, and you can add some additional sensors on there. It's also got the FM transceiver in it, which is that silver device there. We use that as a transmitter for our FM modes, but we also use it as a receiver for our command and control, which I'm going to hopefully demonstrate later. It has a BME 280, which is a pressure, temperature, humidity, and altitude sensor. I actually recently found a bug in the software for that. I was testing it in Denver, and I was expecting to get a nice high altitude reading, you know, like 1,800 meters or something, and I got 137 meters. And I thought, that's strange. So sure enough, it was the code was wrapping around, basically. I didn't allocate enough bits. So anyway, we'll fix that soon. It's also got a MPU 6050, which is a 3-axis gyro and accelerometer. And we've also just recently implemented some new code. Somebody wrote some code to implement the yaw, pitch, and roll capabilities of that, which is kind of fun. So as you change the orientation, you can see those angles change in real time. So again, we'll hopefully demonstrate that. But that was actually done by one of our community members, implemented the code for that. And it also has a quick connector for adding additional I2C sensors. So these days, you'll see a lot of sensors on Adafruit and SparkFun. They have this quick connector, so you can just daisy chain multiple sensors without having to solder. So we have 2 of these quick connectors, one that lets you add sensors to the Pi 0, the other one, this one here, allows you to add it to the Pico. So that way you can add additional sensors without having to do soldering, which is nice. So the solar board, this one is used to connect the solar panels to do your charging of the batteries. And we use 6 different INA 219 current and voltage sensors. So that way we have lots of different channels of telemetry to look at. And a fun thing you can do is if you put it on a turntable and rotate it in front of a lamp or in the sun, you can see the current and voltage peaks as each solar panel faces the light source. And you see it go to 0 as it faces the other way. And you can do things like you can estimate the spin rate, you can figure out the axis of rotation based on the relative amplitudes of those. So these are fun things that people do with real satellites in orbit and real satellite telemetry. And for the CubeSat Sim, we use extremely low-cost solar panels, or about $1.50 each. So these are not like the ones that we fly on our spacecraft. Actually, these solar panels are pretty robust too. I've actually never broken one. I've tried hard, and I've built dozens of them, but they've always held up. So our battery board, we use 3 nickel metal hydride cells, AA's. People always ask, well, why don't you use lithium batteries? They last much longer and the like. Well, for one thing, with nickel metal hydride, we can use a very simple charging circuit. In fact, it's not really a circuit at all. It's just a diode. If we just basically charge this with a 5-volt source from a USB or from our 5-volt solar panels. The other reason is that nickel metal hydride batteries are very safe. I have students build these. I've had students who have been soldering them with the batteries in, and I've had students that have shorted them while that was happening. The traces glowed like a toaster, basically, but nothing bad happened. And once I unbridged it, the batteries actually still function. Okay, so that's an advantage that you do not have with lithium batteries. Other people have actually implemented lithium batteries for longer lifetime, but I like the nickel metal hydride. It's also good too that you don't have to worry about shipping it. Right? If you have lithium batteries, it needs to always be declared and it needs to be shipped surface. And we shipped loaners and all kinds of things around. So it's good for that. So for the ground station, years ago, Burns and I developed the Fox in the Box version 3 Raspberry Pi image, and I think that's been a pretty good success. I think a lot of people use it. It not only has Fox Telem, which is where Fox in a Box gets its name from, but it also has the other ground station software that's needed for the CubeSat sim. So that includes Direwolf for APRS. It includes QSS-TV for slow scan TV. It has a WebSDR, which is a nice, very simple user interface. The thing I hate the most about SDR software is that it's like really hard to figure out. Right? The first time you use a new SDR, it takes you about an hour to get sound out of it. Right? You've got to find all the magic clicks and settings in order to get it to do anything. With a WebSDR, it's one click, and you get that beautiful static sound as soon as you go, which is really what you want. Right? It's a radio. You want to get sound out of it. It's got Cubic SDR, RTL SDR, gpredict. We're currently doing a beta of Fox in a Box version 4, and that has the very latest version of Fox Telem. It also has SDR++, which I really like actually. SDR++, it's fully open source, and it has the same interface across Windows, Mac, and Linux. It looks identical, which is good for students. Also, this new Fox in a Box version 4, it works on a Raspberry Pi 5 because it's bookworm. There's still a couple little bugs in it, which is why it's still beta. So if you're collecting telemetry from the in-orbit CubeSats, we still recommend the version 3. So the CubeSat sim, it used to have 5 telemetry modes. Now it has 7. We added a new crossband repeater mode and a FunCube mode, which emulates AO73, AMSAT UK's awesome CubeSat that is still flying around out there. So it's very useful. So I'm going to try to demo both of those modes today. So some of the things that we've done over the past year with the CubeSat sim. Because about this time last year was when we released the version 2 hardware. We had a year of beta and we released it. Making some very small changes to the hardware now. We did do a version 2.1 software, which added these new modes and also improved the command and control. So that's what I'm going to be demoing. And in there we have a beta 2.2 right now software. It's pretty minor, but it improves the simulated telemetry. And it also has this neat mode where you can simulate failures. There's 10 different failures that it will simulate in the telemetry, and you can do exercises where you've got to go through Fox Telem and figure out what's gone wrong with the satellite, basically. So we've been doing a lot with kits, as you might have heard. We've had these blank boards available on the AMSAT store for many years, where we put the surface mount components on, and then there's just through-hole components. But we've been doing kits now for 2 years, and where we get the boards actually assembled. So it's a kit in that you still need to stack the boards, and you still need to put it in the frame, and you still need to attach the solar panels, but there's no soldering. And it takes between 1 to 2 hours, depending on how handy you are, to put it together, and you have a fully functional CubeSat sim. So it comes with everything, including the 3D printed frame. We unfortunately did have to increase our prices because of tariffs, because everything comes from China, and we've done about 100 so far, and they sell out extremely quickly. We've always sold all the ones we brought to Hamvention, and we also sell them out on the AMSAT store often within hours of them going up. We do an announcement to AMSAT ANS about a week before. So if you're interested in getting a kit, make sure you're following ANS so you see the announcement as to which day they're going to go. We did 40 of them this year for the ARRL Teachers Institute, which I'll talk about in a bit. And we're also planning to do one more batch this year, which might show up in the store in December or in January, depending on how that goes. We also developed this year loaner kits. So we've had loaners for many years where somebody can borrow a CubeSat sim and ground station to do a demo, to do a presentation, to put into a classroom. The loaner kits are the same, except you have to put the CubeSat sim together yourself. So the students or the group can have the activity of assembling it for 1 or 2 hours. So it's kind of like a 2-day activity. 1 day to build it, and then another day to actually use it in the classroom. And we've done some testing with that. It was tried by the Mount Carmel High School Amateur Radio Club. Those students in San Diego were just great. So these are available now. We have 4 regular loaners and two kit loaners, which anyone can borrow if you're going to use it for a demo or take it into a classroom. Just need to get in touch with me. So talk a little bit about some of the partnerships that we've been developing. We've been working with ARIS for a number of years, and Frank mentioned a few of them on his presentation yesterday. There's the Sparky, which we provided the ARIS Radio Pi, which is basically the Fox in a Box software on the Pi Zero, and also the STAR project. I'm going to show a few slides on that later. And I mentioned the ARRL with their Teachers Institute. I'll share a little bit about that. And also, one example of our partnerships with science museums is the Cox Science Center and Aquarium in Florida. They currently have a CubeSat sim on display there. So we're working towards that. And hopefully we'll do more of these. If you know anybody in a partner organization or at a maker fair or science museum, just feel free to put them in touch with me. Happy to help them out. So one thing we've been developing this year is the new version 2 of the CubeSat Sim Lite. So you might remember a number of years ago we had light boards, which is just a minimal board that only does the transmitter part. It doesn't have sensors, it doesn't have battery, it doesn't have solar panels. All the telemetry that it does is all simulated. So now we're doing a version 2. So this is what the version 2 looks like. So it's just this tiny little board that plugs into a Pi Zero. But it's got the FM transceiver in it, it's got the sound card in it, so that you can do command and control. You can basically do everything that you can do with the full-sized one. And it's obviously much cheaper, just being a single board. So we're going to hopefully have these in the AMSAT store next year. And also, we have we use an attenuator circuit to keep the power output down to 50 milliwatts. Because when you have your transmitter right next to your receiver, you don't want to transmit a lot of power, otherwise you blow everything up. So we use that attenuator, but if you want to, for example, fly that light board on a balloon, on a high altitude balloon, you can just bypass the attenuator, and then you've got 500 milliwatts of FM power, which is actually enough for a balloon flight. So a little bit about what the Teachers Institute did. This was a lot of fun. This was part of their space communications and radio astronomy class. So these are teachers that have already been through one Teachers Institute class where they've gotten their license and learned the basics of ham radio. So now they're coming back for more. And they spent nearly 1 day of their week building and using the CubeSat sim. And I think they enjoyed it. And they all got to take their CubeSat sim home with them. And hopefully they'll be taking it into their classroom this fall and spring. So we're hoping to get some feedback for them. What did you do with it, and the like, and keeping in contact with them. So here's a couple photos that the ARRL provided, so you can see. Nice setup there. She's got her 3D printed frame parts there, and her board stack is built and ready to go. They use the no solder kits for that. Others, like some people do workshops where they solder them, but you need to allocate more time for that. And here's another shot here. You see he's adding the solar panels and following the wiki instructions. So this was a good experience. The ARRL was very happy with it, and hopefully we'll be doing it again next summer as well. So one thing we did this year, we've had a quick start guide for a while. We refreshed it for the latest hardware and software, and we added 3 new ones. So we added a ground station quick start guide, we added a crossband repeater one, and we added a command and control one. So these are single page, double-sided color, and we print them out with the loaners, but anybody using them can just pick this up and figure out how to fly this thing pretty quickly, hopefully. So we also developed this year some activity guides. So here's the problem statement for activity guides. It's, I just built or borrowed a CubeSat sim. What do I do with it now? Right? I mean, it's great. It's fun to look at. It's fun to hold. It makes beeping, buzzing sounds. But what do you do with it? So that's what we did activity guides for. So they're step-by-step instructions on how to do some kind of a STEM activity. And they actually work with a CubeSat sim, or you can do many of them with the light. Just the telemetry is simulated. Some of the activities are really easy, just like listening to the sounds and looking at the waterfall. Others are more challenging. For example, running FoxTelem and picking out, reading the values, interpreting what the information is. The activity guides include questions so that it can be integrated into a classroom, so that there's some interactivity. And we're releasing them with a Creative Commons with attribution license. So anybody can edit them, change them, incorporate them into whatever. They just need to say, these are originally from AMSAT. That's our only requirement for that. So we're hoping that the teachers do that. So they've been under review this summer. And so they've all been done at least a couple of times. So they're available on GitHub now. We have 10 different ones available to do, and hopefully more. And we plan to record videos to make it easier to see how to do them. So here's an example one here. This one is for the MPU gyro, and these are the other ones that we have developed here. So there's quite a few of them. The last one's kind of interesting, the MQTT Adafruit IO activity guide. That's kind of my favorite one. I'll just show you what that one looks like. Some of you are probably familiar with MQTT as a protocol that's used in Internet of Things. It's commonly used to distribute sensor data from a small device and get it into the cloud. So what we do is we run different software on the Pico, and we use the Pico W so that it can connect to your local Wi-Fi, and then it publishes it to the Adafruit MQTT broker and to their cloud, and they have nice tools for generating real-time graphs. So you can actually see your sensor data in real time, which is a lot of fun. And the Adafruit account is free. All you need to do is update your software, and then you can run MQTT on anything. The one example there is that's a MQT tool is a iPhone MQTT app. So anyway, you can. This is an example of a more advanced activity guide. The other ones are not as advanced. So the CubeSat Sim, it's been in the classroom quite a lot this past year. I used it myself at Villanova University. It's been at Johns Hopkins University, University of Texas, Dallas. Augustia here is going to present on that right after me. Also, it's being used at Iowa State University and probably other places too. So it's starting to get out there. It's also been to a number of events, Hamcation, Hamvention. Special thanks to Jack, Karsten, and Dennis, who ran the table at Hamvention since I wasn't able to be there. It's been to the Frontiers of Flight Moon Day. It's been to all different places. Nick Pooge, is Nick here? Here's Nick, yeah. And Garth Likens, who is your lab manager. Is that right? Yep. Have borrowed it and used it for a lot of their STEM outreach as well. So yes.
You mentioned that Karsten was also at Huntsville this year with his CubeSats.
Oh, I need to add that. Yep. Okay. So Karsten, who's Drew's son, demoed it at Huntsville as well. Yeah. So I don't know if you're watching the AMSAT UK colloquium last weekend. I was watching the YouTube. Their keynote speaker, Patrick Wood, has built a CubeSat sim. You can see it there in the picture. It's actually got a really nice dipole antenna. It's also got an ultrasonic sensor on it that he uses for demoing. But he did a live demo. Also, you see in the middle there, he has a flat-sat version of it that runs, and he mounts it on a board. It's kind of cool. He also has a little screen that interprets the telemetry for it. So that was a really nice demo. You see he's running Fox Telem over there. And his demo mostly worked, so it was good. We'll see how I do. So just a little bit about our work with ARIS. So this is the STAR program, and they've just switched to a new robot. It's meant to simulate a Mars rover, where you control it remotely using commands. And you can either control it just using Bluetooth, or you can send commands over APRS, which is pretty cool. And this rover is nice. And what they do with us is they added a CubeSat Sim Lite running in SSTV mode, and it sends you pictures from the rover's view, but updated every 30 seconds. So it's got a nice long delay, just like if it was coming from Mars. You don't get full real-time video like that. And they've actually integrated it. You can see it on the right-hand window there. They've integrated the QSSTV open source code, so it's actually in their dashboard. So this is going to be nice. This is what the robot looks like, and this is the view in the front there. You see the PyCam up on the right there. So this is going to be interesting, and they're actually talking to SparkFun about getting this integrated into the frame of the robot itself. So we'll see how that goes. Okay, so one other thing I wanted to mention was that we have a new AMSAT Educator's Guide, and this was actually the idea of David Vine. Is David here? Oh, David, he's all the way in the back. He's working hard there. So it was his idea because he was looking to gather information, and he was, searching through my wiki and pulling up documents. He's like, we need one document that's got everything in it. So that's what this is. It's like 120 odd pages, and you see the table of contents for all the different things. And it's kind of a good idea. I mean, once you hear about it, you're like, yeah, of course you need one big document with all this stuff in it. You don't have to, follow 20 links and download different things. So anyway, so we put this out there. I'm sure we're going to change what's in it. We're going to improve upon it, but this is a good start, and I'm really, really glad that we have this out there. And we can share this with people, and they can just go through it and figure out, what's the information that I want. And it includes some of the youth initiative information in there. It actually has Frederick's SatNog's information in there because that's closely related, and lots of other things. So excited to have that out there. Okay, are we ready for a demo here? Let's give it a try. Okay, so I have my ground station here, which is Fox in a Box Beta version 4, and I've got my radio here to my Quansheng, and I'm going to launch the CubeSat Sim here by taking out the Remove Before Flight tag, of course. And when it comes up, it will transmit its call sign in CW and then start. And I have Fox Telem here running, ready to go. Okay, it's transmitting. We don't hear anything though. It's interesting. Okay, demos never work. It's guaranteed. Let's see. Oh, by the way, I have the Fox engineering model here. So I'll leave it up here till lunchtime, so anyone wants to take a look at it. What do we got here? Got a green light, but no blue light, so I'm gonna use the push button to force it into FSK mode. Maybe that, there we go, that sounds better. Okay, we got a beautiful sound of noisy telemetry there. Okay, so we are running. And if I just click here, we should get a lock. Yep, that's good. We have a nice open eye. You can see a good digital signal here, so that looks good. And if we go in here to FSK, we should see some, yeah, we already got one packet. And let's see, the battery is 3.88 volts. That's pretty healthy. That should survive our demo here. Now, the solar panels, we're only getting like 1 volt because, you know, there's just overhead lighting. In the sun, we would get better voltage there. And then here under experiments, these are the payload sensors. So you can see it's 22 degrees Celsius, 46% humidity there. These 3 numbers here, 1, 2, and 3, this is where we're transmitting the YPR, the yaw, pitch, and roll. So, oh, I forgot to deploy the solar panels. Here we go. Okay. Okay, so the fun thing about a 2U is you can fit these bigger solar panels. And once we did that, we realized, we could put them on hinges. And so, and actually you can get about 400, 500 milliamps of power out of these solar panels. So I'm going. Sorry? Did it? Yeah, it did too. Yeah. Yep. Yeah, you'll see a slight voltage spike if you're like really, really patient. But you notice the plus Z is 3.71. That's the strongest because it's directly under the light there. Okay, so we are going there. So I'm just gonna turn it here, which should change the yaw. So we'll see if that value changes from 0 degrees there. There it goes. Yeah, what is it? 325 degrees? Turn it around the other way here. Go that way. Okay. All right, so let's do some command and control here. In the past, I usually change modes using the push button, but let's try some command and control. If you notice here, it says command and control is on, and it is DTMF or APRS. So I'm going to first use APRS. My Quansheng, I have it flashed with software that lets it transmit SSTV and APRS. So let me do that. Mode for that. And what this should do is this should cause the beacon to turn off. If this works, let's see if it does. There we go. Beacon is off. So we are saving power here. And it's just a toggle command, so if I send it again, see if we come back. Maybe. Yeah, there we go. All right. Demos work. Amazing. Okay, so that's APRS. It's just a simple packet. You just put mode equals in the text, basically anywhere in the packet, and you can set the mode or turn the beacon on and off. So I'm going to change it to BPSK mode, which is mode 3. So to do DTMF, and by the way, I'm just transmitting on 435 megahertz. That's the frequency it's listening. So I'm going to key up and send DTMF 3 pound. and that should switch it to BPSK mode. So let's give that a try. Key it up here. Okay, it looks like it did it. Actually, if you look, when you send a command like that, the green LED actually blinks as if you were doing the push button, so you can tell. I can't see it from here. That looks promising though. I need to change the mode here to BPSK, and let's see if that works. It's thinking about it. Yeah, there we go. That is BPSK, and it just locked in, and we should get telemetry again here. And there's also, see this ground commands? It keeps track of how many commands. So as you're sending the commands here, so I guess we're up to 4. I tested it once this morning, and then we've done these. Okay, so far so good. So let's try a new mode here. Let's try the FunCube mode. So for that, I'm going to transmit 7. So let's go here, 7 pound. See, okay, it turned off. So FunCube actually uses BPSK 1200 bits per second, you know, just like our BPSK mode that we used for Fox 1E and is used in the LTM these days. However, the bits are not the same. So what you'll see is, if you're looking at it in Fox Telem, you'll see every now and then the eye will sync, and then it will lose it. It's off a little bit there. A little bit noisy there. Every now and then the eye should sync up. There it goes. You see the eye sync there? But you hear the distinctive beep. It's one of my favorite things about the FunCube telemetry is that you can always see it in the waterfall because it's got that distinctive beep, and you can always hear it. You're never guessing which satellite is it. You're like, oh, that's FunCube. It's got the beep. It's good for students too, because students are like, oh, you know, this telemetry just sounds like noise. You know, not that exciting. But if you got a beep, that's something to listen for. Okay, so this is FunCube mode here. So in order to decode this, we need to use a FunCube decoder, and that uses the FunCube dongle. And this is actually software that AMSAT UK developed. It's still experimental right now. I don't know why that should have quit here. Let's quit that. And we'll see how it goes. We actually emulate JY1SAT, which is a Jordanian satellite, I think, that uses the FunCube software. We chose that one because in addition to sending telemetry, it also sends an image as well. So if we get a piece of an image, it should show up here where this AMSAT logo is. Hopefully we will get it. I think we're still transmitting here. Yeah, we're still transmitting. Sometimes it takes a minute. In the meantime, I can show you what it looks like here. So this was shooting out my balcony yesterday. You can see the mountains in the background there. And so you have the telemetry here down the bottom, and then the image. And the cool thing is that it uses SSDV format for the image, which is basically a JPEG transmitted digitally. So you either get the image or you don't. There's no analog degradation. And in particular, you can see it if you zoom in a little bit here. You can see that the top right corner is missing, right? It's just a block that's missing. And then down the bottom, like the last line was missing there. So it's interesting to compare. You can see the analog SSTV versus the digital SSDV mode. Let's check back in, see if we got something yet. Nothing. Okay, typical. I can hear it. It is still transmitting. Okay, well, we will give up on this. Don't want to take too much time here. Don't know why it's not locking in. So let's try. Our last demo here is crossband repeater. So I'm going to switch to that mode. So I'm going to bring up the WebSDR here. And I'm also going to bring it up in my browser here. Let's see. So the crossband repeater, it receives at 435 megahertz in the 70 centimeter band, and then it retransmits at 144.9 megahertz in the 2 meter band. So let's see if it works here. Just thinking about it. Yeah, I'm on the right Wi-Fi here. Start. Okay. See why the ground station software is beta here. It is thinking about it. Ah, there she goes. So I'm going to tune it to the 2 meter band here. So I'm going to switch. I'm going to set the squelch, and I'm also going to do the same thing here. Okay, all right, so crossband repeater mode is mode 6, so I'm going to transmit 6 pound. Okay. Okay, so 144.9 is what it's transmitting on. You probably see the blue light is off right now. Now it's just waiting for a carrier basically at 435, and then whatever it receives there, it will transmit. So let's give it a try here. KU2Y. All right, it's working. You can hear a bit of digital delay in that, but that is working. So that is the crossband repeater mode. Okay, so I think that will be the end of my demo here. And I do have some beta instructions on how to do the 2U. We'll be formally releasing this next year. But basically, you can upgrade any CubeSat sim to a 2U just by printing 3 new parts and getting some additional hardware. Our frame is currently modular. That's why it has little holes here. These little holes in the post there. That's so you can connect them. So you could even build a 3U if you wanted to make a golf ready to go ahead of time here. So, so you can get involved in the CubeSat Sim project if you want. You could borrow a loaner, just get in touch with me, or you can build one yourself, either a kit or if you like soldering and 3D printing, do the whole thing yourself. You know, happy to have you involved. I'll take some questions. I probably have, yeah, just maybe a couple questions. Yeah.
I'm just wondering if you can swap input and output frequencies for the crossband repeater.
Yeah, you can't actually because we're using the FM transceiver chip, and we buy the 70 centimeter version. I mean, I guess you could buy they do make a version of it that's 2 meter. It's the SR105V. So yeah, I guess you could if you swap, but you have to swap out hardware. It's not just software.
Okay, thank you.
Any other questions?
I have a question.
Sure.
Yeah, you didn't mention the current costs. I know they change from each
Sure.
time that the
Yes.
kit's released.
Yeah, so the kits now are $550, everything ready to go. We sell the blank boards for $35. I think we're almost losing money on those now, but we're selling the blank boards, and then it's about $350 in parts if you want to order everything from DigiKey and Amazon and put it together yourself. So those are the basic costs right now. And then for your ground station, you just need an RTL SDR, right? That's like $40. And then you can install the software on your machine. I like this touchscreen Raspberry Pi screen that also has a speaker built in. That's good for the ground station. Yeah. Any other questions? Okay, thank you very much.
I'm gonna, while you're presenting, I'm gonna have to come up and hook up the power supply, okay? So just ignore me when I come back on that.
But is the HDMI working? Seems like we're having some trouble getting this hooked up to the HDMI.
Did the cable get unplugged on your? Here, plug the power supply in.
Oh, there we go. Okay.
Sorry about that. Good morning. I am Agastya, KJ5 MSH. Today I'm going to be talking about the CubeSat Sim workshop that I helped organize at my university, the University of Texas at Dallas, over the summer. So today I'm going to talk about who was involved behind in this workshop, what all we did to prepare for it, what kind of activities we had for our participants, and also what the participants thought of it, along with our future plans with the CubeSat Sim, which I'm a PhD student, so it involves research. Okay, so starting off, the person behind who brainstormed this workshop is my PhD advisor, Dr. Kankuk Ji, at the University of Texas at Dallas. So a little backstory. I am a computer science student, and my advisor is also involved in cybersecurity research. The second person involved was Dr. Robert Bauman, who is a nationally renowned expert in radiation physics and semiconductor design in harsh environments. He's also an IEEE fellow. And I also received help from other students. Timothy's in the picture on the right. And then I had a lot of help from Alan, who spoke before, from the president of our ham radio club, Ron, and then all of the other people named who helped me solder all the kits, which took a lot of time. So you might be wondering, why are these computer science people doing a satellite workshop? We didn't want to be your run-of-the-mill typical satellite workshop. We wanted to have some interdisciplinary efforts because having various people and their various ideas come together, that's where we have cool ideas for participants to take part in. One of those cool ideas was cooking our CubeSat Sims in an X-ray chamber, which we'll see come up later. The cybersecurity interests, that's more so related to the safety and reliability of a satellite in low Earth orbit based on the atmospheric not atmospheric, but the cosmic radiation in that environment. So I will say big shout out to that link. Lots of valuable information there. Lots of information gathered by or curated by Alan. So for the workshop, we purchased 10 CubeSat Sim kits. One of them was the prototype that I built beforehand for the workshop, as well as to get my hands set in soldering, because I'm not an engineer. This was my first time soldering. And then we also had six kits pre-soldered for the workshop, which were to be assembled by students. So for the planning phase, this was, as I said, the summer of 2025, a lot of tariffs. Lots of parts were either out of stock or they were outrageously priced. So Alan's bill of materials, which I have a screenshot of here, it lists a lot of alternatives for most of the parts, which was really helpful in helping me track down alternative suppliers. Some of the activities that we did, two of them were gathered from Alan's activity guides, which he talked about before. So we did, namely, the basic telemetry activity and also an advanced telemetry activity from those guides, and also the X-ray activity where we killed 2 CubeSats in an X-ray chamber. During this phase, I had to fast forward through learning RF basics because at that time I was not, I was also new to ham radio in general, so I didn't know what AFSK stands for or what it does. Sorry. Next year, for when we repeat this workshop, I'm planning on having more activities based on everything that Alan's fleshed out in his activity guides. So, as I said, we bought like 10 CubeSat sim kits, and I used 7, like 1 for the prototype and 6 more for the participants. So it was like 7 boards that I had to solder, or 7 kits of boards that I had to solder. And the first prototype, it took me several hours spread over 2 days because this was my first time soldering. But it was a really, I'd say, an enjoyable and relaxing experience for some reason, even though I burnt my fingers like 3 times. And then I got like plenty of help from the other people organizing this workshop who sat down with me to solder like the battery boards and the solar boards and etc. But I will say, if you are planning on recreating a workshop of a similar scale or larger scale than what we did, then please sort out all of your parts beforehand. It'll make fishing for everything much easier, instead of like blindly rummaging through all your DigiKey bags. So about the student demographics, we didn't just focus on like electrical engineers, right? You can see out of like the 20 participants we selected, okay, most of them were like computer science majors, but a lot of them were also in like mechanical. And there was one who was like a biomedical engineer for some reason who was interested in doing this. I don't know why, but they had a lot of fun with it. And we also, okay, most of our participants were bachelor students, but we also had a decent number of like graduate students. I think about 3 of our students had ham licenses already, and our word had spread to South Korea for some reason. A student from South Korea's KAIST University was flown out to attend our workshop, which is pretty cool. So, as I said, best satellite workshop at UTD yet. It was a 3-day affair. We had planned on basically filling up each day with activities and informative lectures and also free food. Students were tasked with assembling all the models of the CubeSat sims from the boards that I had painstakingly soldered before. And they were also responsible for setting up the ground station that you saw Alan demo. And a lot of students had their first interaction with ham radio. So, day 1 of our workshop, we went over small satellite basics, things like what is a satellite, right? What kind of orbits, at least around Earth, you can find a satellite in. what are small satellites specifically. We also went over things like TLE, the format, and how to track a satellite using, I believe, NORAD. We also talked about how these days there's been a there's been a large upsurge of using COTS in small satellites because there are more and more companies who are trying to cut costs in their satellite designs. And the CubeSat sim is also representative of that because, obviously, you have to make the CubeSat sim cheap, otherwise no one will buy it, right? So we also discussed that there was a large gap between cybersecurity and aerospace. My PhD advisor, Dr. Kankukji, he has prior experience launching a satellite in the past because he was involved with IBM's Endurance mission. And those guys, I believe, they launched a scientific 6U CubeSat, or maybe a 3U one, I forget. So when he was involved with that, he noticed this large gap between cybersecurity and aerospace because a lot of the aerospace people, they could not come up with good answers for his questions on how reliable or how secure will this satellite be when it's in space. So as a way to bridge that gap, I guess that's also one of the motivations behind organizing such a workshop. And the first activity that we planned for this day was to have all of our students assemble the CubeSat sims. So, yeah, this is basically what I went over just now. So what I'll be focusing on mostly towards the latter half of this presentation is cybersecurity research in space. And also, with respect to how reliable COTS can be in a harsh environment. So how applicable can a CubeSat sim also be or as a proxy for a real satellite? Because a CubeSat sim uses pretty accessible parts. So will it really be a good stand-in for a realistic satellite? Okay, that aside, on our second day of the workshop, we also continued with CubeSat sim assembly, but we also made the students start assembling install their ground station things, and we had them be familiarized with the Fox-Telem interface. And the first activity we did was an RF essentials thing as well, after all of that had been set up. So you can see the waterfall behind the professor here. So lots of students, they enjoy taking selfies of themselves with SSTV. And one of them even went so far as to making their ground station desktop wallpaper their selfie. And the other activity we did was the advanced telemetry activity from Alan's guides. So in this activity, we basically placed a CubeSat sim on a turntable, and the turntable would spin around, and the CubeSat sim placed on it would also spin around. And based on the direction we pointed an LED light or an LED lamp at it, you could see the voltage change, the YPR of the CubeSat sim also change. So students were quite interested in this activity because they were trying to wrangle with Fox-Telem and see the kind of graphs that it produces for each of these quantities. So day 3 of our workshop was, we had a change of venue. We moved to our Center for Harsh Environment Semiconductor Systems. If you look up UTD chess, you'll get a very different result. You'll get information about our chess team, which is not what this is about. But so That over there is Dr. Robert Bauman. As I said, he's a IEEE fellow, expert in radiation physics. He's also been involved with TI for like several decades as someone making their chips for space environments, etc. We had a talk about space debris, also like radiation 101, like what is a TID, what is a single event effect caused by cosmic radiation, what kind of, how do you characterize those things on a hardware level, especially in semiconductors. And then one of the things we discussed was the need for shielding, but the fact that shielding is not a one-stop solution for everything, because the more shielding you add, the more weight you add to your satellite, which increases costs, and that's probably not good. So about the final activity where we cooked the CubeSats. So this is all just information leading up to it. As I said, we went over a lot of information on radiation. So Dr. Bauman, he discussed how radiation is a very common cause for satellite mission failures, because a lot of companies, they rush through their planning phase and they don't really account for how radiation can basically break their satellite, and that leads to a lot of wasted money. So based on this, I'll talk about this later, but there should be some form of software level validation or testing to see how radiation affects a satellite. So for our final activity, here's the setup. We had, so I do show a laptop over here, but we actually connected the CubeSats with wall power with a current reader in the middle. Yeah, so we placed our CubeSat sims on that fourth shelf. Yeah, the shelf 4. So 2 CubeSat sims. One of them would be shielded with an aluminum bucket. The other one wouldn't. And we would see which one dies first. Yeah, so this is just a calculated amount of like how much dose of X-ray both CubeSats would get. Seems like I forgot to put a picture of the CubeSats, but it's all right. Yeah. So, spoiler alert: the shielded CubeSat survived. Okay. So, based on student feedback, what did students like about this workshop? Surprisingly, none of the students had anything bad, or unsurprisingly, none of the students had anything bad to say about the CubeSat sim itself. All their complaints were about our logistic planning phase, because we didn't have enough screwdrivers for everyone. So a lot of them had to share, which basically they had to like wait for other teams to finish before they could like start with theirs. So that's something we will keep in mind for our next year's workshop. And a lot of students, they found the CubeSat Sim project to be really cool. A lot of them wanted to buy it for themselves because we didn't let them take them home with them. So a lot of them were interested in getting involved with AMSAT. I'm not sure how many of them stuck with that interest though. But as I said, this is a great activity, educational activity for hams and non-hams, because like you're building a freaking CubeSat, right? Like it's cool, right? And as I said, like people loved SSTV. One student suggested making a GNU radio plugin for the ground station software. I'm not sure how far he got with it, but it did seem pretty promising. Another student, as I said, wanted to buy their own CubeSat sim to build from scratch. And here are some other activities that students suggested for like future iterations. So, future plans. my professor and I are planning on making a smaller scale workshop for high school students. I think it's going to be either in later this month or maybe next month. Hopefully I'm not too busy by then. Medium term, so next year, we're going to have a newer and improved summer workshop with more activities, and hopefully we'll have more students participate as well. Oh, fun fact, we also had like one faculty member apply for the summer workshop, but for some reason we didn't take them in. I don't know. So long term, this is something that our computer science department had been cooking for a while, because we do intend on offering coursework related to satellites, especially with a cybersecurity perspective, because we have had NSF funding for this. I believe the NSF is quite interested in satellite education for undergrads. And also, I'm a PhD student, so I'm going to do research with this. So, basically, my aim is to create a suite of software tests to capture parametric shifts of performance, latency, etc., and basically all the functional failures of the components that make up the CubeSat sim. And we want to test the whole system. So all the literature I've seen so far, it's either just hardware level testing, so they don't care about software, which I care about, or even if they do test with software, it's only like component-wise. It's not like a system-wise effort. So it's a lot of words over there. Yeah, so far what I have going for this is, yeah, so this is the block diagram that Alan has put up on the wiki for the CubeSat sim, but I wanted to do even deeper parts enumeration and go even deeper into each of those components, especially like the computer, the Raspberry Pis. So yeah, this is all the enumerations I could come up with for the Pi Pico. So we also want to eventually switch out the Raspberry Pi Zero with the Pi 4 because it's more performant and probably would be better suited for our tests. So all the parts I could come up with for the Pi 4. Pi 5 as well, because, okay, so at least for the Pi 4, that is a drop-in replacement with the CubeSat sim software. If I wanted to put in a Pi 5, that would involve updating the software to a newer Debian version, which the CubeSat sim software does not support out of the box, and that needs like some work, which I'll probably get around to it at some point. Yeah, these are all the other sensors and like solar stuff. So what have I tested so far? Just the SD card. So I wrote a little script to monitor the SD card performance. You can even you can like look at it at that URL over there, and eventually I want to whittle down to a minimal set of components that can effectively characterize when a CubeSat sim is going bad under radiation. So this is just like a web app I created to see like what the average read time is, write time, median read time, number of bit flips that you can toggle from that side control panel over there. So, I mean, none of these CubeSat sims as of yet have been put into the radiation chamber. We need more authorization for that. But so we haven't really noticed any bit flips in normal usage, unsurprisingly, obviously. But eventually, later this year, we want to change that. We want to add more components to look at and to plot them out and see how the trends vary over time, especially when subject to radiation. So far, this is the basic statistical inference I could come up with. So the total test time is largely dominated by write time, unsurprisingly, I think. if you know how computers write to.
We got you back.
Thank you so much. So yeah, some of the challenges. Sorry, what? Sorry about that. Yeah, so some of the challenges that we've come up with, as I said, the Pi Zero is too weak for running software tests because it has less processors and less RAM than a real computer. And also the Pi Pico it does not have its own OS, so it's like slightly harder to measure or to just write software for it. And also it may not be realistic as a real satellite's OBC. And as I said, like Pi 5 is our eventual goal because a Pi 5, you can attach an M.2 hat to it so that you can plug in an SSD to it, which is more reliable for storage. Yeah, so the primary blocker for the Raspberry Pi 5 is that it requires Debian 12, while the CubeSat Sim only supports Debian 11. Yeah, so that's all I have for my talk. You can access information about our workshop in the second link over there. But other than that, if you have any questions. Sure. Yeah, I think so.
So in the units you tested, what failed, and how much shielding did you put on the one that didn't?
Okay, so the shielding was just a simple aluminum bucket, probably like less than half an inch thick. Yeah, so basically what I noticed, the parts that failed in the CubeSat Sim that failed, it was the Pi Pico, the SD card, that was totally corrupted. And some of I believe the gyrometer and the temperature sensor, those things failed. No. Yeah, it was gone. Next question.
How similar is X radiation to radiation that you'll see in space?
So X-ray radiation, that's a good question. X-ray radiation in the chamber that we tested, it will simulate TID radiation, which is total ionizing dose. And that, I think it represents like the gamma radiation in like a cosmic environment fairly well. But obviously, like the radiation in the chamber, it like comes from a point, whereas in space, like it's all around you, right? So.
Couple of comments. One is, are you aware that with the Fox class satellites we launched, we had radiation experiments as part of the mission?
Oh, really?
Vanderbilt University installed experiments on our satellites, and we downloaded that data using our Fox downlink capability, and they have written up papers based upon their findings on the experiments. So you might want to take a look at that.
Interesting. I'll have to talk to you about that later to see where I can access this data.
Yeah.
Several PhD students got it.
Okay. I
Yeah,
see.
several PhD students. And the second comment is I'm intrigued as to what precipitated your interest in doing a CubeSat simulator workshop at UT Dallas in the first place. What was the spark that created the interest in doing it? And second, you're mentioning high school students and potentially doing a workshop like that. can ham radio operators join one of these workshops? Or do you have to be a student in an institution to qualify, or what?
Okay, yeah, okay. So your first question was, okay, so at least for the high school workshop, that we are organizing it with a company, and those guys, they have selected, or they put out like applications with a high school, and we're bringing some of those selected high school students to do our workshop. Otherwise, if you want to participate in a workshop like this, I'd encourage you to apply maybe to our next year's summer workshop. And what was your first question? Oh, the Spark, right. We received an NSF grant.
That's money.
Mhm.
How do you translate that money into an activity? What's the linkage that got you involved with CubeSats?
Okay, so this is actually the second iteration of the summer workshop we've organized at our university. The first one was last year, and I believe it was just something that was brainstormed. I was not involved with the last year's workshop. This was something that was brainstormed by my professor and the president of our ham radio club at the time, and they came up with this idea to basically do a CubeSat sim workshop. Yeah.
Okay. Agustia, thank you for coming
Of course.
and presenting this. Hopefully you come back again soon and share your research.
Mhm.
You guys did a great job with this workshop, and you basically made your own kits,
Right.
right? Because you ordered all the parts and you put them together, so the participants just did it. In the future, hopefully, people running workshops can get in touch with me ahead of time, and we can actually place specific orders like we did for the ARRL. So it could be a lot less work in the future. Another comment is that maybe you can incorporate the CubeSat Sim Lite next year,
Okay. Yeah.
being the low-cost boards, and that way maybe they could even take home a Lite with them when they finish. So something to think about.
Okay. Gotcha. Yeah. Those are good comments. Thank you. So I yield to the floor.
Is this audio is working that good? That's good. Let me get it up a little closer here. My name is Larry Ryan, W7DGP, and I want to talk to you about my experience building a CubeSat simulator. And you see my two on the side. I built a version 1 and then a version 2. And from the Seattle area in the state of Washington, I believe these are the only CubeSats floating around in Pacific Northwest, aside from one third one built by my friend W7DLH in Portland. Yes, that Portland. And so that makes 3 of them in the Northwest. And so all of the photos that you see are mine. I'm talking about my personal building experience. So let's see if that works. So why did I build a satellite? I've always been interested in them. I got my start working for NASA after getting out of the Army and seeing the moon landing. Got me very excited about space. And I started right away trying to get a job with NASA. It was not easy, but it eventually came to pass. And so first thing they had me doing, being with more of a RF telecom engineer, is put me in charge of this beautiful VHF array that you see here. And remember, this is during Apollo. This is in the olden days when satellites were made out of marble and teak wood and things like that. And so it really piqued my interest, and I started learning about tracking mostly, and then about data, that kind of thing. And so I became KL7 Hotel Golf Radio and got to experience living in Alaska at the same time. So my first ham satellite was Oscar 6. That was my beginning. So from all of this, I was kind of hooked. And the satellites I tracked were big monsters, not CubeSats, like this monster. And check the kick motor. And okay, I always say I still have my AO40 black armband. I put it on every now and then. And I had a lot of antennas and equipment set up and working into JA from Seattle area on AO40, and life was good for a while. Well, that brought up something I didn't expect. Let's see. I'll get rid of that. But most of my satellites were designed to support the Apollo project and studying of cislunar space. Satellites that were launched and put in big elliptical orbits. And so I kind of have to watch what I'm doing with the mouse here. But anyway, I want to talk about the build, and there's a considerable amount of assistance that I found that made building a satellite, the CubeSat simulator. I want to know how many here have built one. Okay, that's quite a few. And I would invite anybody watching this presentation to take a shot at it. And one of the things that really helped was this bill of materials, because it was not a kit. I could purchase the boards, I got that, and then sourcing all the parts is always an engineering problem. And but in this case, it really helped. And that's kind of where I started right here. And then there are the assembly instructions. And notice it says, in these steps, you will start building. And like, okay, having a problem with this website? Download a PDF. Print it all up if you want to do that. So it's kind of an invitation to get the project going. Here's a bill of materials, here's the instructions, and on top of that, you even have videos. And you have Alan's very clear instructions and narration as he is building it. And I didn't follow all of the videos, but there were some of them that really helped. I wanted to see, well, how do you orient the board for this? How does this part actually go in here? And I watched the video a couple of times and said, oh yeah, I get it. And little helpful hints as far as the actual assembly goes. So, and here, this is the version 1, and some of my photos are version 1 because all of the photos, unless I specify, are all mine on my workbench. So I wanted to say this is the authentic thing. And one of the things you can do is, as you put things together, you can do intermediate testing, and that inspired me to get out some of my Arduinos and make up a few test fixtures. Because along the way, it's a good opportunity to learn about all the various components. And over here, you see I could test the software. So I plug in the SD card, plug in one solar panel, and then the battery board, which is pretty easy to assemble, and put that together, and then log into my Raspberry Pi and do some testing, and just kind of a mid-course testing and verification. And while I was at that, I thought, well, I'm learning a little bit about all the various sensors, and so that was a good opportunity. And then you can put together your stack and the frame, and it starts to look like a satellite, and that gets it's very encouraging. So my second CubeSat sim was the version 2 or 2.1, and there are newer versions out, as I've learned this morning. And this is basically the layout. This is an AMSAT photo, not my photo, but showing that version 2 has a lot of exciting things on it. The first thing I noticed, the transceiver chip, and so I immediately said about that, and I think these boards I got for free very early. And I saw Alan's posting that if you're interested in this, and so I fired off an email right off the bat. And so that was my start. But there's a lot of capability. The version 2 was, we could call it version 2 exclamation mark. And so it also is a group of parts, lay it all out. And these are photos from my workbench. And one thing that came in very handy, I don't have a 3D printer. And it seems like everybody I know has one, but I don't. And so I found that the CAD file, I could send that into a 3D printing company. So I did a little shopping, found a 3D printing company, said, okay, send us your CAD file, we'll turn that around in short order. It was like about a week later, I had these frame pieces that you see here on the left, and I asked for them all in a different color, and then I didn't know what kind of plastic. I just checked ABS, and that was fine. And these parts came, and I snapped them together by hand, as you see on the right, and all the holes matched up, everything like that. So I thought, we're off to a good start. And it was. And you can see my old Tektronix oscilloscope there. So that's my bench, my 465. And so there are a lot of more modern, smaller scope, but I did use that a little bit in probing around and trying to verify everything is working properly. So I have these are the completed version 2 boards that I did, and there are things I learned about, like the Raspberry Pi, oops, got to back up. Okay, the Raspberry Pi Pico, I had never used before, but I read about it considerably and looked at YouTube videos, that kind of thing. But this is my chance to learn about the Pico along with all the other parts and pieces. So I kind of welcomed that. And get to this point on my second satellite, and I really felt heartfelt thanks to Alan, because along the way learned that the software, the hardware, the design, the whole effort on the CubeSat simulator was very, very well supported. That's my experience. This is not a Heath kit. Some of you built Heath kits a long time ago. You open that box, everything was there. And in this case, it's pretty much the same. Everything is there. It's online. And if you run into a snag, you can send an email to Alan and you get a reply pretty fast. So it worked very well. And so then you begin to put things together. Becomes pretty much a step-by-step process. You can go back and correct mistakes, kind of thing. Then there's the ground station, which is just as interesting. It's all software, but still it's part of the project. And so what I did is I purchased this RTL SDR dongle, and I got the full package. And you can see here the antenna. And so I bought it. It comes with the antenna and this nifty little tripod. And I already had the FunCube dongle. I have both versions of that. I purchased those a long time ago. And but I wanted to try this this particular SDR. And then there's Fox Telem, which I'd never touched, and I thought, free software, and how's that going to work out? And Fox Telem installed perfectly, and they have different versions of that, and ran very well on my laptop. So I used my laptop, and the software and this particular SDR. And things worked the first time. I fired up the satellite. I had already logged into the Raspberry Pi and put in my own call sign. And so when I fire it up, I hear W7DGP and CW. I'm mostly a CW op anyway. I thought, that does make me feel good. It's mine. And so the best ground station is Fox in a Box, and Alan's already enumerated all the software, and it is a ground station in a box. And I happen to have a Raspberry Pi 5. I've done a lot of Raspberry Pi projects, so I took out my Pi 5, which I had become bored with previously, and loaded the ground station software in it, the version 4. It just kicks right in. I had no problem with this. And we don't want to confuse that with Fox in a Box Escape Room in Seattle. And there's also one in Portland, Portland. And so it comes together then. Here's my completed satellite. And it has 2 antennas. So that part still impresses me because it receives and transmits. And then the Fox in a Box telemetry, and these are photos taken on my workbench, everything up and working very well. And I was able to demo this and talk about demos, and I've done a lot of demos in my life, and you're right, a lot of them fail. But I demoed this at the Seaside Convention, CPAC Convention 2025. And it came off without a hitch. And this is with a bunch of fellow hams, and the crossband repeater got people on their feet. And I used for the receiver my little IC705, and so I punch up the crossband repeater, and it's working, and that got a lot of interest. It was a pretty good sized crowd, and it came off without a hitch, to my relief. So have a lot of respect for this. And so the final assembly is getting the board stack to fit the frame pieces, and that was my personal challenge, and it's more of a mechanical challenge because I had no challenge with the software. Software ran okay, and there are a couple of ways of adding the software. If you don't want to mess with things too much, you can buy an SD card with the software on it, simply plug it into the Raspberry Pi and kick it off, and that's how I did my version 1 satellite. And the version 2, though, I decided to clone it off the GitHub site, and it was a good idea because, in speaking of software, there's a lot of software, they write it. Now this is a criticism of the computer science people from a double E, all right, is that they write the software, it works, it's version 1 maybe, something like that, and then that's it. All the software developers go on to some other project. Not in this case. This software is continually being updated, upgraded, modified, corrected, and I have full confidence that the software I have in my version 2 CubeSat is continually being observed, updated, refined, and I can add things to it. So the finished CubeSat then, it's there on my bench working like a champ, and it's kind of fun as an individual to play with it, but I've carried it to schools and 2 different high schools, and as I mentioned, the CPAC convention demonstrating it there. And the way that I demonstrated at the school, I just kind of hand it out, you know, kind of worry about it, say, don't drop it and don't pull that red tag till I say so. And I just let the students launch the satellite. And there are a lot of things you can show. A lot of, not science classes, but there are a lot of engineering classes in high schools these days. And high schools are involved in what's called FIRST Robotics. And I've been a mentor in FIRST Robotics for 17 years. So I've been dealing with high schools all over the Seattle area, Western Washington. And so I demonstrate it to robotics clubs in the high schools. They're already used to sensors or remote sensing and software-driven hardware. And so the CubeSat simulator then is something of very high interest to them. Okay, lessons learned, and this is the meat of this presentation. And to talk about the build versus the software, and the bill of materials is kind of the secret sauce of this, other than Alan's support, which is also the secret sauce. And one of the things I didn't know what octopart meant, but later figured it out that I could have made good use of that, and I've learned something. And then the intermediate testing helped me identify bad parts, and also I was able to learn a lot about these various components. I've dealt with accelerometers before, but they were, you know, $10,000, $20,000 units, and but here I have my own accelerometer, and I can test it extensively. So I made a lot of test fixtures. Another thing is quality soldering. I've been soldering since I was 14, which is how old I was when I became WN7DGP. So, and I've had a lot of training in soldering, and I've also developed coursework and published it on soldering. But you need to do your best work on this one. And getting the board stack to fit the frame is my personal challenge. And I can make excuses like those headers, the plug-in headers, stacking headers, come in many sizes, not necessarily the size you should be using. And then in version 1, I had the wrong header soldered in. Yeah, all 40 pins. And so after making careful measurement and using my flush cutter, trimming the length of all the pins, I got that to fit in the frame. And so that was a lesson to me. Like they'd always say in the Army, it's brain lubrication, cutting all those pins. And then modifying the build, adding things after. It's the version 1, that's it. The version 2, though, every time I go to the AMSAT website, I see something written by Alan that, yeah, we can do this. I think, I want to do that, like command and control. It's not that difficult to add functionality to it, I found. Okay. Then in software, all the software is provided. I can do programming, and I'm basically a retired nuts and bolts engineer. But when I was working, my last years of working with Hewlett-Packard, I was writing scripts, documenting scripts, in mostly the Unix environment, and there's no getting away from having to do a little bit of program, but I always resented it. And so I'm not anxious to have to go through a bunch of code or debug a bunch of code, but you don't have to here. all software is written, and there's something up with the software. I have shot off a email to Alan. Alan comes back with, yeah, download this version, so we're up and going. And as far as Raspberry Pi, this was project 15, I say. I think it may be more like project 20, really. But so I'm very comfortable with working with Raspberry Pi. Things like the SD card imaging, selection of the distribution, command line, power requirements, setting up a Wi-Fi. I use PuTTY to log in, and they're better ways to do it. So I used all of those skills, and if it's your first Raspberry Pi or your first computer that you're logging in and setting up, that might be a little daunting, but the support is there. If you follow, I was pretty familiar with what I was doing, but I've noticed the instructions in there. If you follow them step by step and you don't skip a step, you can get it up and working and learn something. And I found that I could use my Unix knowledge here and background and old work habits. I could apply them to the Raspberry Pi and kind of make the environment a little more friendly for me, like setting up path command, for example. The other lesson learned here is Fox in a Box, which I resisted for quite a while. I probably used my laptop ground station for the first year that I had the version 1 satellite. But I thought, time to get into that, and I did. And it is awesome. And the only thing more awesome than my Raspberry Pi 5 that you saw the picture of is that Fox in a Box with the screen on it, and I've got all those parts, and I'm going to make one when I get home like that. And I learned about the Raspberry Pi Pico. Very interested in it. Had no idea it used the Arduino IDE, which I was very familiar with, but that was kind of a fun thing for me. So my last, this is the last slide. My latest initiative is to add GPS to the satellite. So I bought these parts. They just arrived not long ago. And so I'm going to add GPS to the payload. And another thing, there's no way to make a slide for that, but I've always been interested in APRS. And so recently I set up APRS on my Anytone handheld and learned a little bit about it. And the satellite makes quite a bit of use of APRS, so there's a learning there. And so it's going to squawk APRS packet with the payload and the latitude and longitude in it. That's my goal. I want to see that. And so that concludes my presentation. Anybody have any questions? Are you ready to build a CubeSat? Well, hearing none, that is it. Thank you.
Okay, ladies and gentlemen, we're going to adjust the schedule a little bit, so let's take a 15-minute break right now, and we will still have a complete program, I assure you. He turned it on?
He clicked on something, it popped up that little thing.
You know,
Yeah, it's great.
So today, I made the connection. You know, David.
via incentive licensing. I mean, I was out of the country. I was engaged in other things. And so this guy broke into my QSO and says, "You're in the wrong part of Canada. What's that?" And so then I just shut everything off. And I was living in Seattle. So I made my appointment, take the extra cross exam, and went and took that.
All right, if you guys can take your seats, we'll get started back up. All right, next presentation is Bringing Orbit and Classroom SatNOG's CubeSat Sim. Frederick Robb, he's already up here ready to go, so let's get started.
Good morning. I'm Frederick Robb. I'm a STEM instructor focusing in aerospace applications, which include CubeSats, high-altitude balloons, rocketry, and I work mostly in the middle school, high school, and community college level. I've been involved with Alan for the past 4 years on the CubeSat Sim and probably SatNOX for 2 years before that. So basically what I'm going to do is show how these two projects interrelate to each other and build off of each other, and also introduce the idea of adopting a satellite. I don't have to tell you anything more about the CubeSat Sim. I think we've seen enough this morning. The point that I make to everyone is that it's a fully functional satellite. It's just not space-worthy. Don't need those two. Don't need those three. SatNOX. How many people here are familiar with SatNOX? Oh, and almost everyone. Okay, so this is a review. As you can see, it's a global network of Earth stations, ground stations, operated by educational institutions, hobbyists, space enthusiasts. It's got pretty close to global coverage, which is important later. Large number of satellites up there that they've got data collected from. This was from September. The other thing I'd like to point out is that most of the modes or most of the most common modes for SatNOX are transmitted by the CubeSat simulator. The other important thing is they have dashboards available for many of the satellites, so you can visualize this data, right? And so this is kind of similar to Fox-Telem's dashboards. So basically, anyone can get access to the database and the dashboards for free. You can go right now to satnox.org and view data and work with the data. For $150 US, you can basically build a SatNOX station. All you need is a Raspberry Pi and an SDR kit. I placed this in my house to basically show a worst case station. So when I talk to educators, I say, you know, if you've got a classroom window with a view, clear view to the sky somewhere, you can get a station up and running and receive data from some satellites, but obviously not all. But what's more important is once it's on the net, then you can schedule across the entire net. And there's some really high-powered receiving stations out there that you can take advantage of. So, adopting a satellite. So once you put your, first of all, almost everyone I talk to says, oh, we want to get a CubeSat in orbit. I go, well, what are you going to do with it? Well, they usually don't know. What are you going to do with it after it gets in orbit? Well, you basically need to continuously monitor its health and collect scientific data. So if you're a typical university, you got one ground station, and what, you get 1 or 2 passes a day out of it? And so with SatNOX, you can pretty much get universal coverage, okay? And so rather than build a satellite, or even if you are building a satellite, I'm advocating that you adopt an existing on-orbit satellites so that the students can get the experience of being the, a CubeSat operator, right? So using published information, a lot of these educational satellites already publish information on their net, on their website. Students can learn a lot about the satellite, again, as if it's their own. And then you use SatNOX to schedule observations over a 1 to 4 week period to collect the data and then later interpret the data and then present information to your class about your adopted satellite. So the problem with SADNOX, as I see, is you get this telemetry data, but you have a very difficult time relating telemetry to the satellite's orientation and behavior in space, right? And so that's where the CubeSat Sim comes in. Because with the CubeSat Sim, you now have a controlled environment where you can change variables one at a time, so manipulate the CubeSat and see how the telemetry changes on FoxTelem. So this is an example of the CubeSat Sim spinning on a turntable and the various plots you get from the output of the solar panels. And you're going to see these similar type of plots in SATNOX as well. You also see orientation plots from the IMU. And so now you can actually interpret how that satellite is being positioned in space from the telemetry data. The other thing is, well, there's three things where I see there's an overlap between the CubeSat Sim and SATNOX data. The first is the solar cells and power management. And so with Alan and other people, have developed these classroom activities. And so what this slide is doing is kind of relating how some of those classroom activities then can be used to interpret the SATNOX telemetry data from the solar cells and power management point of view. The second one is basically the orientation of the satellite and the spin rate. Then the third is radio communications and decoding the protocols, right? I've already talked about how many of the common protocols are on SATNOX satellites or CubeSats in general are being implemented or demonstrated, used by the CubeSat Sim. So when you first get involved with SATNOX, I mean, I started off with SATNOX, and you know, I radio amateur, but you know, all these waveforms were new to me, and so SATNOX has a lot. You know, they got a great wiki, but not a lot of instruction, and so trying to interpret how these data is encoded within this waveform was a challenge for me, right? And so with the CubeSat Sim, you can now, again, control this. Because when these satellites are doing passes, they might have a minute or two worth of data. That's really not enough time for you to look and figure out what's going on. The other thing I want to do is point out this last slide showing the Doppler shift. That's turning out to be a really significant thing with SATNOX. Because if your satellite is, the SATNOX receivers automatically tune to compensate for Doppler shift. So when you're looking at the satellite you're wanting to look at, you get really nice straight line. And when you start seeing Doppler shifts, it's either terrestrial interference or it's reception from other satellites, because we got so many satellites up there now. So it's not unusual to see 3 or 4 satellites in your waveform. So for teachers, this is how I explain how to adopt a satellite. First, you want to go onto satnox.org and look at the data, read the wiki. You want to assemble a minimum station and start scheduling some observations so that the teacher gets familiar with it. Ideally, I like to see students assembled in teams of 3 to 5. Then each team basically picks a satellite to adopt. They learn everything they can about the satellite. And then this is the important thing. They work together to schedule downloads over the network for a period of time so that they can really collect some data on it and look at performance. And this is what they're going to have to do if it's their satellite, right? So then finally, the real thing is that they present their findings to the class. So this is basically what you need to build a station. Everything you need is on the wiki. Like Fox in a Box, basically you can just download and flash the image to the card, to an SD card. So which satellite to pick? Basically one that has a dashboard is probably very useful. If you want it to be currently active, you want to make sure it's been received by numerous stations. You want satellites that you can find out information about on the internet. And ideally they have six months of on-orbit data available. And so these are a few examples. And the IIS is a great one because it's really easy to receive. even with that minimum receiver sitting in the window. So these are some things that we would ask the students to do and to monitor and to look for. I won't go and mention them all. So I wanted to talk for those who aren't familiar with SatNox. You can schedule observations, what they call downlinks, or they call downlinks observations, either by your station, and basically you get a list of all the satellites that are going to be passed within your, overhead, or you can schedule them across multiple stations. And again, this is most useful for doing the satellite observations because you want to have a list of stations that are geographically distributed. So you can see I've got one in Virginia, in the Netherlands, here in California, London, Taiwan, Switzerland. So I've got, my virtual ground station network. This is a typical observation, a very good observation. The signal's strong. You've got those like green and red buttons off on the right-hand side. That's how you vet to tell the database whether it was a good observation or not. In addition to this, you can listen to the signal. So you can listen to the voice communications on the voice, amongst hams on the FM birds. And here's your data protocols, or your raw data, I should say. If SatNox can actually decode raw data, they automatically mark it as a good signal, right? And then if the owner of the satellite has published the telemetry data, then you can create a dashboard that actually tells what these bits mean and translate it, right? So here's an example of a dashboard which actually shows several days worth of data. And what I like about this dashboard is if you look at the bottom line, that's the altitude. So this is a satellite that is deorbiting, which is, I think, was pretty cool that you can see the death of a satellite. Okay. So the real excitement is tracking these newly launched satellites, because almost every rideshare mission, data about those satellites is published on the SatNox bulletin board or forum and make it into their database, okay? And so there's a lot of comments going back and forth. And so there's bragging rights for being the first person to receive the satellite data or the first station. But more important, it's providing a real valuable service to the CubeSat satellite owners, especially the educational owners. And most recently, the last IIS release was like 6 CubeSats, educational CubeSats, and they all come out in the same orbit, right? And so they're just like 3 or 4 dots on the sky. And so there was an incredible amount of traffic going back because, they get identified as object A, object B, object C. And so trying to figure out which satellite is which. And so by knowing what the frequency is and what the modulation method was, and people would compare to Doppler tracks and use software outside. I mean, these are people with really high-powered stations and big Yagis on rotors. And I've just been learning so much about how to identify satellites like this. And I got involved with identifying these little thumbsats. And the organizer had published their TLA, and it's like, why is all this CubeSats in a line like this and yours is over here? Something's wrong. But anyway, so again, this is kind of an advanced exercise, but it really would get the students excited because they can also often watch the launches. Almost all these launches now, they actually will show the deployment of the educational satellites, right? SpaceX, it's a Starlink satellite. Once it lands, no one cares. But with these educational satellites, they all want to watch their satellite be deployed in space. So here's a quick summary of the various learning objectives. So in conclusion, I really think that the CubeSat Sim gives you the experience of building the satellite and a way of interpreting the telemetry data. SatNox provides telemetry from on-orbiting satellites. And so basically you can be a satellite operator without the expense and risks of a launch. So, any questions? Comments? Well, thank you. Thank you for your time.
All right, if you look at the schedule, it says we're on break, but that's because we're a little bit behind. All right, next up we have Burns Fisher with telemetry for Fox Plus and Golf CubeSats. Yeah, I know.
So, I was gonna use mine.
You're gonna.
already talked about it. Brett, you want me to use it? No. You can? No. Okay, so we're not gonna have one. Okay. Okay, fine. You can do it. Okay, and there's a laser too?
I don't think so. Oh, that's an IR reader.
Thought he was reading it, so, okay. Okay, wrong one. Thank you. Knew it was there somewhere. Yeah, I always make some notes because I will typically forget things otherwise. And it's nice to see all of you here. The last time I did a talk, it was at the Ham Exposition in Massachusetts. I've usually given a talk there that's, what's new with AMSAT? Or something like that. And I got tired of doing that, so I gave a kind of technical talk. 2 people came. So, nice to see you all. So I'm Burns Fisher, WB1FJ. I'm a life member of AMSAT. I volunteer as the lead flight software developer for golf, and I've recently taken on Fox Plus. So one thing I want you to know is that I've talked about telemetry before. I think it was 2017, but that was a long time ago. And when I talked about it, it was before we'd used any of these features. They first appeared in Fox 1E, and Fox 1E hadn't even launched. Similarly, HuskySat was the other one that had that. But we already talked about how we define flight software in a spreadsheet and spread it out between the flight software, the telemetry in a spreadsheet, and spread it out between flight software and FoxTelem. So I'm really not going to do any of that kind of stuff. I just want to show you what the telemetry looks like, how it's organized, and I've got some screenshots of what the current versions of the Golf FoxTelem screens and the Fox Plus FoxTelem screens look like. So, as I've said any number of times, the basic flight software hasn't changed since Fox 1A, which is AO85 in 2015. Actually, the biggest changes came with Fox 1E and RadFXSat 2, which were AO109. In 2021, it was launched. And with HuskySat HO107. On those satellites, we switched from an FM repeater to a linear transponder, which made some difference in the software. We were doing a lot of stuff in the software to recognize the startup tones for FM that we could take out, for example. We switched from 100 bits per second, yeah, not many, data under voice, DUV, and that was in the FM satellites. So if you have listened to one of the Fox FM satellites or worked it, we get kind of a lot of complaints about, well, this sounds kind of gargly, and well, that gargly sound was the telemetry that was under your voice. But it was great. I mean, it worked so well, and you could still, of course, very clearly make out QSOs, because after all, it's FM. But anyway, we made that switch to 1200 bits per second BPSK, which Alan was talking about earlier. We added support for the CAN bus internal to the satellite. CAN bus is the bus that has been used in automobiles for ages and ages, but turns out it's getting to be more popular in satellites and works very well. We added secure commanding. People have talked about cybersecurity, and our commanding is now encrypted. Well, I'll say authenticated is really what it is. And we started out with this very low-speed telemetry, and went to high-speed telemetry, but we don't actually have all that much more data to send. There's still the same measurement devices and so on, and things that we want to send. So what do we do with all this extra data? We use whole orbit data. We put whole orbit data in it. And I'm going to talk more about that in the next talk, but I'll just say that's what we do with that, a large amount of that extra data. So what the telemetry, starting with Golf 1E, with Fox 1E and HuskySat, and it will be going up through Golf and Fox Plus, the BPSK is about 10 kilohertz down below the transponder passband. And BPSK, if you're not too familiar with it, it's essentially a sine wave that we modulate on the carrier. Well, it's single sideband, so there's no carrier. And if you go like this, it's a sine wave. If you, at the zero crossing, you suddenly go up again, you've reversed the phase, and that's a 1. If you don't reverse the phase, it's a 0. So the nice thing about BPSK is that it doesn't take up a lot of bandwidth. Let's see, did I miss anything? Oh, yes, I did want to say that this is typically in our satellites, it's been in the UHF downlink band. Golf T will have a 10 gigahertz experimental downlink for testing things, but I'm only going to talk about the UHF downlink stuff, and at this point, we're not putting this kind of telemetry in the 10 gig downhertz. Okay, so what does this telemetry actually look like? The basic unit of telemetry in our satellites are frames. A frame is a fixed size. It contains 669 8-bit data bytes. Why 669? That's a weird number. Well, the reason is because we use Reed-Solomon forward error correction. And in particular, we use the Reed-Solomon 255-223 version. And that means that you send 223 bytes of data and 32 bytes of check bytes that can actually fix some of the data, some of those 233 bytes if they're wrong. Well, 669 is 3 times 223. So there's actually 3 check blocks for each frame. So each frame within it has a header, and the header is also a fixed size. It indicates which satellite, because sometimes we have more than one satellite in view at the same time. And you need to know which one, and Fox-to-LEM needs to know, did I change that? Yeah. Fox-to-LEM needs to know which one to decode and to place in the, as I've now started to call it, dashboard. So it indicates which satellite. It indicates a frame type number. So there are multiple different types of frames that we'll talk about in a minute. And it also includes the satellite mode as well as other data. Satellite mode being, is it in health mode, is it in safe mode, is it in science mode? And the other data Hemir talked about yesterday, which, when we eventually have, long commands, then this data will tell which commands have been received. So each frame ends with one of these check blocks for the FE forward error correction. Each frame also has a CRC, and each frame is a fixed size. You might ask, why do you need a CRC if you've got all this forward error correction? And the answer is that any of these checking things, a CRC is 32 bits wide maybe. I've got 32 bytes of checking data, but there's lots of different possible main bits of data that could result in the same check block. And just think of a parity bit, right? A single parity bit, half of the data that the parity bit is parodying on would be correct. So you can get incorrect data, and we have occasionally had Fox-to-LEM correct some data that was coming down, and it still wasn't right. So the CRC is yet one more check that we can say, no, this is not real. We'll just throw it out and say we don't know how to decode it. So, as I say, a frame is a fixed length, but each frame has a frame type. A frame transmits in a bit over 5 seconds. I think it's really 6 or 7. And within the frame, there is contained 6-ish, and I say ish because it contains 6-ish variable size sets of data that we call payloads. And of course, if the payload is variable size, you might sometimes fit more, you might sometimes fit less. The frame type number tells which payloads are within that particular frame. So an example of payload, current health data, minimum health data, maximum health data. So the minimum and maximum for each individual item. Let's say processor temperature, the minimum since it's been reset and the maximum since it's been reset. Infrequent data, diagnostic data is there sometimes, and whole orbit data, which we'll talk about more in the next talk. Obviously, the flight software and the ground software have to agree on what frame number 5 means. And so, Chris and I work closely together, Chris Thompson, the Fox-to-LEM fellow, and he has been wonderful about making Fox-to-LEM such that I can actually personally change it without changing any code. I can add new items. I can change where they're located in the telemetry. So, part of what I do is set up the telemetry for a particular satellite, and eventually I will check it into his GitHub repository, and then it'll be able to go out in public. Frames are not always filled completely by payloads, so sometimes there's a filler, and I think, oh boy, on my computer this worked right. But you can see that, well, maybe you can't really see that what we're showing here is each different type of frame and how much they differ from 669, and therefore how much you have to put in, like safe data 1, which is in the upper right there, is actually 660 bytes long. So we have to add in just 9 bytes of filler. And you know, just an idea of what this frame looks like. It represents a frame with 5 payloads. The physical sizes don't represent the data size in this picture. The header that you see at the top there is only big because I put 3 lines of information in it. It's really the smallest thing typically. So each payload can be different, but most are longer. The CRC is only 32 bits, for example. So this is the general idea. So some examples of payloads within frames. And the numbers at the top are just the names of the types of payloads. A real-time payload, which is the data that has just received from the sensors in the satellite. Min and max, which I talked about a minute ago. Science data. Now, that's one of the big changes from satellite to satellite, really. Depending on what science payloads we have, science data can do different things. In MESAT-1, science mode was supposed to be downloading pictures. The same in FOX-1D. At other times, it has downloaded different things. Whole orbit data, diagnostic data, and the diagnostic data is typically stuff that doesn't change much. So it's fairly small and we don't send it very often. So it might be, well, why did the processor reset the last time? That's the kind of thing that's in diagnostic data. So here's what the frame types look like as you're looking down. Frame type 0, we'll just call it, is all wide. So it's got payloads 5, 5, 5, 5, 5, 5. I guess there are 6 there. Frame type 1 is real time, and that's got 1, the real time, and then some whole orbit data. Frame type 2 is min-max. It's got min and max and a whole bunch of whole orbit data. And oh, by the way, we'll stick a diagnostic in too. Frame type 3 is safe 1, and it's got real-time min-max and some whole orbit data. And safe 2 has all whole orbit data and 1 diagnostic. Now, so what I mean by safe mode or safe type is that is the data that is sent when the satellite is in safe mode. We go into safe mode when the battery is too low or there's some other problem. So when we're in safe mode, we want to be sure to send the information that we need to figure out what's going on, what the problem is. And so we typically get two frames every 2 minutes. So we try to make those 2 frames count. But notice that all frame types contain some whole orbit data payloads. You'll see why that is in a little later. But we want to get a lot of whole orbit data payloads down. So some frames can be sent less frequently or in different modes, as I said. In the normal health mode, we send those real time, all WAD, min, max, and all WAD and all WAD. So, you know, in normal health mode, we say, okay, send one of these, and then 5 of these, or whatever the number happens to be. In safe mode, we send safe 1 and safe 2. There might be a safe 3 and back to safe 1 that we do 2 minutes later. So note that these are all like just examples. The frame order is pretty easy to change in the flight software. It's really just an array with numbers in it. Okay, do 1, 1, 1, 2, 3, 4, 1, 5. You know, trivial to change. But the point is, if we're in safe mode, we want to be sure that we're sending information that's needed. If we're in health mode, we want to try to get as much information down as possible. If we're in science mode, We will only rarely send the health data, but we'll typically send as much science data as we can for our science customer. Okay, so you have seen some FoxTelem stuff from the CubeSat sim, and that's great. I wanted to show you some FoxTelem displays from the satellites we will actually have in orbit. And these are screenshots from my home system, and they are screenshots of my FlatSat. I have a FoxTelem, I have a Golf T FlatSat. So my bench is kind of covered with components with wires screwed from one thing to the next, but it can produce the actual golf telemetry. And now this may change because, hey, it's in my office, I can still recompile stuff. But it can, FoxTelem obviously can support a lot of satellites, but there's only a single RF screen, and this is it. You can see the bottom is the spectrum display. Again, you saw that with the CubeSat sim. The black on the top left that is showing the actual modulation. And remember I said it's a sine wave that changes phases every once in a while. And if you look there, you can see it kind of looks like a sine wave, but every once in a while there's 2 up bumps or 2 down bumps, and so on. So that's the actual modulated sine wave that's coming in. Then on the bottom, the blue line is showing the 1-0 bits that we're getting out of it. I actually forget what the red line is. In any case, the eye diagram on the right is showing that the 1s and 0s are decoded. So if you get a 1, the line goes up. If you get a 0, it goes down. So if you have lines that are going across the middle of the eye, that means there's something kind of screwy. And the phaser on the right really wants to look like that sharp line. If it's spinning, then you're not locked in very well. So that's what the FoxTelem RF screen looks like. There are a few other things on it up near the top with telemetry format and what device you're using. In this case, I'm using a FunCube dongle to receive my golf stuff, the center frequency, and various things on the right to show what you want to display. Okay, so this one is a display that is, let me just, yeah, up on the top there, you can see there are tabs. One of them says input, and that's the current one. One of them says Fox plus A, and one of them says Golf T. So those tabs are how you get to the dashboard for a particular satellite you want. And this particular one is the dashboard for Golf T. And so it's under the Golf T tab showing the health information that we have. It's still under development. Not all the values, not all the numbers you see there are correct, because not only do we have to figure out where we're putting the telemetry within a payload, but we have to say, okay, 0 to 255 means minus 20 to plus 110 degrees centigrade, and then put in the appropriate decoding information. So this is not all correct, but the thing that I want you to notice really is that there are 12 different panels there. They have different sorts of information, and many of them are pretty specific to Golf T. So, for example, if you've heard Golf T talks in the past, you may remember there are 2 different onboard computers. One onboard computer is the old, it's not old, the legacy processor, legacy IHU we call it. That is the processor that was in all of the Foxes, and it's in the LTM, and it just has a lot of space experience. The other processor is called the RT-IHU, radiation tolerant IHU. And we have not flown this before. So what we wanted to do was to make sure that we didn't totally lose the satellite if this unknown to us processor failed. So Golf T has both the LIHU and the RT-IHU in it. And what you'll see over here, boy, I wish I had a laser. That's the legacy IHU information. You can see there's temperature information. Is the transponder enabled? Is that the LIHU that's in control? Because it might be the RT-IHU that's in control. Various things like that. Where is it now? Right, on the bottom left is the RT-IHU information. And the RT-IHU has two, it actually has 4 cores, but let's not go there. It's got essentially 2 processors within each RT-IHU. And so we can see the primary temperature. The secondary temperature is the primary active. If not, then it's the secondary. The primary status of memory and so on. Is it this? Oh, Robert said it wasn't a laser. Oh, okay. Cool.
Don't poke your eye out.
Right, yeah. Okay. Yeah, so, and there are other boards. The CIU is another board in the in Golf T. The SDR radio has information about it. We have another set of VU radios called the DCT that's part of the RT-IHU, and this is information about that. Let's see, and a bit of special min-max information about when was the last time it was reset, when was the last time it changed. So a lot of stuff here on Golf T. Now within, let's see. Yeah, so this one is Fox Plus A, and I actually just finished that. And you'll notice it only has 9 panels. That's because it has nothing about an RT-IHU. It has nothing about the SDR or the RT-IHU's radio. Instead, it has a number of panels relating to the ISIS power supply, which is something that we've never, sorry, ISI space. We don't want to say ISIS. So all of these things are ISI space stuff because we haven't used them before, so we want information about that. And then up on the top are similar things to what you saw in golf. But I really want to particularly emphasize that between those 2 tabs, and I said I just finished Opera working on this, I did not change a line of Fox2Lem code. Fox2Lem is written in Java. Didn't change a line of code. It was just CSV files that you changed to make this work. And great thanks to Chris Thompson to make all that stuff work. So as I keep saying, we'll talk about whole orbit data a bit more in the next talk. But for what I want to point out now is that whole orbit data is yet another tab, and it looks really similar to the health data. The biggest difference of the health data between that and the health data is that you have more of it because you get nearly the data for an entire orbit as opposed to just when you were going over a ground station. In fact, the whole orbit data is built from the exact same spreadsheet as the health display. Another feature that's kind of interesting in whole orbit data is, it really contributes to it, a feature about Fox2Lem is that you can graph any of these data items. So for example, I right-clicked on the IHU temperature here, and chose graph. Whoops, wrong button. And this is what I got. The temperature is staying fairly steady, although something happened right here, I don't remember what, that when it let it go down a bit. And again, if you do this, you can do this on the real-time display as well, but you'll have more gaps because, if there wasn't a ground station when it was reading that on the particular time that's on the x-axis, well, there's no data there. So I talked about diagnostics a little bit. This is the the Golf T diagnostic display. So this is the IHU reset information. What caused that to happen? The legacy IHU stuff, there isn't too much data from the legacy IHU about what kind of issues it had. But the RT-IHU processor has an enormous amount of data. So that's why these panels are much, much bigger. And there's two of them because there's two processors on the RT-IHU. So again, this is the diagnostics panel, which we don't send very often because it doesn't change very much. There's also, by the way, if you look carefully, right here, it says UTC hours, UTC minutes. We will have a GPS on the Fox-T, and from that we can, if it's turned on, we can collect the time. When we downlink the UTC hours, UTC date, right here you see time and epoch. So we have always had downlinked number of resets and seconds since the last reset, and that was our time. And in order to turn it into UTC, you have to somehow compare one of these dates, one of these spacecraft times with the actual UTC that it matches with. And after that, you can use the normal spacecraft, our normal spacecraft time, and turn it into UTC until the next reset. So this has the seconds, time and epoch right here that this UTC matches up with. So this will save somebody on the ground a lot of time of figuring out when resets happen. Oops. I kind of thought I had yeah, I guess I don't. Anyway, thanks for listening. I always try to put some rocket porn on my final slide. So here's the AO-91 launch on a rocket that unfortunately I wasn't able to visit. Some of us stood out in the cold for several days, and they delayed the launch, and finally said, "No, sorry, got to go home." So we did. But anyway, it's a great picture. But anyway, I think you see that every satellite we build can downlink different telemetry. And it's relatively easy to change without changing the ground software at all. So the flight software has to change to collect different data and so on. But that's comparatively easy. Okay, so I have another talk about whole orbit data and a new use for a similar algorithm for whole orbit data. But if you have any questions about this so far, then go ahead. Jay is.
Whoa, high gain microphone here. Great, absolutely great presentation. But my question relates to flight software.
Okay.
The stuff that's actually on the bird.
Yep.
Now, there's going to be two CPU chips. Let's keep it simple. There's the legacy chip and the new chip. Now, is there going to be, or is there planning to be a provision that if one chip fails, for whatever reason, it's off in the weeds, it's doing something it shouldn't, or it's gone dead, it's brain dead totally, that it will not take down the other chip, that the other surviving CPU will detect the failure and continue the mission will continue.
Absolutely. That's the whole point of having all these processors. And in fact, some of the RTIHU processor, the one that is not currently working, which is either failed or is in standby, is disconnected totally from the bus. So, yeah.
So, and that failure, so when the one chip goes silent for whatever reason, that disconnection from the bus is automatic?
Yes.
It's not under software control, it's just, it's hardware, it's gone.
I can force it under software control, but yes, if the processor fails, it will automatically switch.
By hardware.
Yeah.
Thank you.
Yep.
And any more questions? If you want to learn more about the Golf RTIHU, I think it was in the 2017 proceedings. So if you go to the AMSAT member portal, they have all the past proceedings posted on there, and you can read up. Zach wrote up a great article on the RTIHU and how it works.
Yeah. Zach is the big designer of that. Cameron back here is working on the next version of it with Zach. So, yeah, we'll have a new version pretty soon, won't we? Right.
Any last questions? Okay, let me get your, oh, you already got it up? You're set.
Hey, I got to do something while Jay's talking.
Yeah, there you go. All right, you have the floor.
Okay. How long do I have till, by the way? Okay, very good. I just want to pay attention. I've talked about whole orbit data before, and Robert just talked about the 2017 symposium. I talked about whole orbit data in the 2017 symposium, but that was a long time ago. It had never been used before because Fox 1E and HuskySat hadn't flown. So this is a little bit of an update on whole orbit data, and so I want to explain to you how the whole orbit data algorithm works, and then what else we can do with a very similar algorithm. And on top of everything, by showing you this, I really want to encourage you to collect telemetry and send it to us. And you will see that we depend on you to get the whole orbit data. And of course, you can also download the whole orbit data for your own Fox2LM version. So what is whole orbit data? You can kind of see the point in this diagram. Satellites are going to orbit over the whole Earth, especially satellites that are in somewhat polar or sun-synchronous orbits. They orbit over the whole Earth, or you could also say the Earth turns under them, but there's a limited number of ground stations. That's especially true over the Pacific and Central Asia. So, there isn't too much here. Unfortunately, this particular picture doesn't show Europe. There's a lot of stations in Europe. And thank you to our European friends for collecting data for us too. Let me also point out this one right here. Where's that? Hawaii, right. We've got one member who has a home on the Big Island in Hawaii. We gave him a Fox in the box, and he has set it up. And so we do get some telemetry from the middle of the Pacific Ocean. We have a few people in Alaska, I think, and we talked to people at the poles as well, but I'm not sure if we actually have any working there or not. But anyway, the point is that there are lots of stations in Europe, some in India, some in the Indian Ocean, and that one in Hawaii. But there's a lot of places where there isn't any telemetry, and we would like to know what goes on. The processor reset over the Pacific. Why? What was the temperature getting too high? Radiation doses, or were we going over, the South Atlantic anomaly or something like that? So anyway, I do want to thank all the hams and non-hams for collecting data around the world. And I hope this will encourage you to do so too. But anyway, what is WOD? WOD means whole orbit data. And the point is, how do we get the data over locations that don't have ground stations, right? And the answer is, we send a whole bunch of data as fast as we can when we are in range of a ground station, even though it was collected earlier in the orbit. But the satellite itself doesn't know where the ground stations are. It's not like each ground station sends a signal that says, hey, I'm here, you can start sending me data. So how do we do this? And the answer is, we send that same data over and over and over and over again. All of our satellites since the early Foxes have had this stuff called MRAM, magnetoresistive something or other memory. It's a special kind of memory that is not very dense, but it is non-volatile. You can turn the power off, you can reset the processor, nothing gets lost. It has essentially infinite write cycles, unlike the SD card that you kind of see here. The SD cards do not have infinite write cycles, even if they're not in a radiation environment. But the MRAM does also have a fairly high tolerance to radiation. The older Foxes, the FM Foxes, used it for the voice of Fox. If you've ever heard Veronica and her downlink, this is Fox 1A. This is amateur radio station Fox 1A. That's her voice was digitized and put in MRAM. We also save the min-max values there and have from the beginning. Since Fox 1E and HuskySat, it's also stored whole orbit data. And MRAM is organized for the whole orbit data as a circular buffer. We typically collect one data set for whole orbit data per minute and store it in MRAM. But you saw in the previous talk, we send a lot of data, of those data packets out of MRAM, so they are transmitted a lot faster. Now, unfortunately, we didn't get this to work. This was a great animation that works fine on a Mac. And what you see is that this is a circular buffer, and the right circle goes chunk, 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 and keeps writing into a slot in the circular buffer. The read pointer goes zoom, 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 zoom. So I think, for Fox 1E, we would send 31 whole orbit data packets per minute, but we only collected one. So every time we collect one, we wipe out the oldest of the previously collected ones. Let's see. Yeah, well, this isn't very interesting since it doesn't work. But now the question is, how much whole orbit data do we actually get to save, or should we save? You know, how much space of whole orbit of MRAM should we use? And the answer is surprising. It was surprising to me totally. No matter how big the memory, we still transmit each whole orbit data packet the same number of times, because it relates to how fast we transmit versus how fast we write. Yes? But so why does it matter? Why don't we just have one slot or something, or 31? And consider, if we have a small amount of memory, a given packet is sent more frequently. So it's still sent the same number of times, but a lot more frequently. So it doesn't stay in MRAM as long, and thus, what? It sees fewer ground stations. With more memory, a given packet is sent less frequently, but it's spread over a wider area on the Earth. So how much memory use is optimal. Carl Wick, N5MIM, was wonderful, and the actual math that he did in his simulation is in the 2017 proceedings. So if you want to look it up, you can. But it's great. He simulated this whole orbit data thing based on kind of guesses for what an orbit might look like, and it's typically a sun-synchronous orbit of some sort, and based on ground stations that we knew were typically sending us data. So he did that simulation. Turns out there actually is an answer, and the answer is approximately 42. No, 150. 150. If you send more, it doesn't hurt anything particularly, but it doesn't help much either, for the most part. So again, each saved whole orbit data payload gets sent the same number of times, regardless of memory size, but it's sent over a larger area. So note that 150 assumes the same number of ground stations that we have typically had. The number has gotten smaller as we've had fewer satellites in orbit that go to Fox-to-LEM. So I do want to encourage anybody to collect telemetry as soon as we have something to collect from. Yeah, go ahead. What's that? Yeah, it's intended not to be factorial, but oh, good point. So yeah, you can see the math that Chris did in the 2017 papers, and Fox 1E telemetry that Carl and I gave in that symposium. Yeah, 150 factorial, that would be a lot of packets. I don't think it would fit in MRAM. So before I go on, I just want to give it credits for the whole orbit data stuff. Carl Wick is amazing. He's a silent type. He doesn't say too much, but he'll hear, "Oh, how are we going to do this? We need something." And Kip can see this as well, and he'll just go off and he'll do something. He'll solve the problem in some fashion or another. So Carl did a wonderful job with this whole orbit data simulation. Chris Thompson, who is the Fox-to-LEM writer, and Fox-to-LEM needs to understand the whole orbit data algorithm too, because after all, you don't necessarily send all the packets in time order. So he has to sort the packets as they come in to make sure they're all in order. Mike McCann, K2 gigahertz, actually had the original idea for doing whole orbit data. So thanks to him. And I'm the one that did the Fox-to-LEM, the telemetry transmissions. So thanks to me, I guess. Okay, so let me go on to, I wanted to talk about how whole orbit data works, because the point of this paper is I found another use for a very similar algorithm. So to talk about this new use, I first want to talk about how much data we need to downlink at different times for the life of Golf T, and what telemetry speeds we have and have to use. So I think I said before, Fox 1A through D at either 100 or 200 bits per second, depending on which slide you look at, data under voice. Fox 1E, HuskySat, MESAT, and so on, anything that uses LTM, including Golf T and Fox Plus, is 1200 bits per second BPSK. And as I said earlier, the amount of data that we collected for these guys didn't change much, so that's what we used that extra speed for, was to send whole orbit data. Golf satellites are a lot more complex. they're 3 times as big, but I think, as Jerry would say, 90 times as complicated. So there's, some health data that's probably a little similar, but then you have all of this stuff, like we have an ADCS, Attitude, Determination, and Control System in the Golf Tee. And there's a lot of commissioning work we have to do. ADCS depends on the magnetic fields of the Earth and knowing where you are for a given magnetic field. So there's a lot of commissioning. You need to send down data that was received in the magnetic receivers. Jerry won't like me to say this, but I suppose we might sometime have future pictures. But there's a lot of data that could need to be sent down. So you might ask, why don't you just make the telemetry faster? Well, we might in Golf 1 in a future thing. But right now, when we first changed this, when we first started, 1,200 bits per second compared to the 100 bits per second of data under voice seemed enormous. So we started out doing what was easy to do with the 1,200 bits per second. And that kind of baked into some hardware designs that 1,200 BPSK. In addition, the LIHU probably could go a little faster, but not enormously faster. So the answer is, as long as we are using some of the legacy IHU hardware, we probably can't go much faster. We might change that. We might very well change that in future processors, future satellites, but not now. So what do we do? How do we deal with 1,200 bits per second and larger data quantities? So let's think about how much data we actually need to send. For an example, for ADCS commissioning, we need raw magnetometer readings. I mentioned before, raw gyro readings, some coarse sun sensor data, and some of this data is collected every 10 seconds for an entire orbit. So, do the math, 90 minutes for an orbit, 66 groups of 10 seconds, it's a fair bit of data, and I didn't tell you how much data was in each packet that had to be collected. And one downlink frame is only 669 bytes. Right, so we don't have, but the other thing about this is we don't have to do it very often, and the data doesn't need to be there instantaneously, right? As long as the data is time-stamped, it doesn't need to be sent immediately when it was collected. So, for example, how do we get all this data from the ADCS? The ADCS unit that we're using actually has a non-volatile memory built into it, and it collects all of its data every 10 seconds regardless, and we just have to ask for it and save it on our own. Let's see. So, sort of a summary of requirements, right? We need to collect data frequently. There's a lot of it. We need to downlink it to sparsely loaded ground stations, but not necessarily immediately. Does this sound a little familiar? It's kind of like whole orbit data, isn't it? So I hope nobody, well, if you're a Mormon, I'm sorry I used LDS as the things here. No, honestly, I do apologize. But LDS I used as large data sets. So how does LDS differ from whole orbit data? LDS is a large quantity of data, but it's limited. So it just doesn't keep going forever. Whole orbit data is continuously collected. With LDS, we don't want to lose any data. We need all that data for the commissioning process. Whole orbit data, if we miss some, well, it's too bad, but it's not a tragedy. The LDS is only done a few times in the mission. Whole orbit data we'd like to do continuously for the entire mission. And LDS, the amount that we're collecting fits into MRAM, but whole orbit data over the life of the satellite is far greater than the total MRAM size. So then the question is, can we modify the whole orbit data algorithm to accommodate these differences? And I wouldn't be here if the answer didn't seem to be yes. So here's how I plan to downlink LDS. And by the way, this is implemented, partly tested on my flat side. It works. So sorry again, I can't run this nice little animation that I had. But the idea is that you write frame-sized chunks of data from the ADCS or wherever it's coming from into MRAM, including a timestamp when it was collected. The amount written has to be less than is available in MRAM, so there's no overwriting. It's just a chunk in MRAM, and that's what we want to downlink. So we collect and write it just once, and when it's done writing, we treat, again, the data as a circular buffer to read from and transmit that same list of data over and over and over and over and over again. The difference between that and WAD is that we never do any more writing until it's commanded to. So we're just sending the same data over and over again. Oh, I guess I got the, yeah, okay. On the ground side, Fox2Lem is, again, very clever about taking time-stamped data and putting it in the correct order. So Fox2Lem to Fox2Lem, LDS looks identical to WAD. It didn't have to do anything different, except that, thank you, Chris. He had to tell me how to make another tab that was that looked like whole orbit data. So it requires adding new payloads, new tabs with WAD-like data, and turns out that was actually pretty easy to do. So, but remember, the ground stations are sparse. Even if everybody here and every member of AMSAT collected telemetry, oh my God, that would be wonderful. There would still be lots of holes. And so how do we deal with holes? Surely we're going to miss some LDS packets. And it's important for LDS. So we could keep sending everything over and over and over and over again. But if we only have 2 or 3 packets missing, do we really want to send 100 packets over and over again? No, that would take a long time. So the solution is that I implemented an uplink command. And the uplink command has the capability of giving 2 different sections of that data and say only send data between here and here, between A and B, and C and D. So in the example here, which you can't see because it doesn't run, I could command it to only send the missing range. So for example, I could tell it only transmit between 6 and 7 and between 9 and 10. And so it never transmits the other ones, all of the other data in MRAM. It doesn't erase it, it just doesn't transmit it, it just skips around. So the idea is that we fill in those holes much more quickly. I don't understand why we're getting 2 of these, but anyway. Oh, I do know. The second time I was clicking, it was trying to start the animation. Anyway, so the summary of LDS is we can collect many thousands of bytes quickly and then send them slowly in small time-stamped chunks. And we repeat sending over and over until most get received. And then we can, when the satellite next goes over a ground station, we can send a command to transmit either only or mostly the missing pieces. And then it's finally done, and hooray, we've got all the data that we need, and now we can send a command for the next thing we need. If we were collecting magnetometer data, we can now tell it to collect gyro data and repeat the entire thing. And then when we get enough information, we can go into the next step of the commissioning of the ADCS. Okay, my rocket porn. I think it's fair to say a lot of the things that we do, like this LDS algorithm, are workarounds for capabilities we don't have, right? That's life, building satellites as volunteers. But, you know, I'd argue that's also life as a ham. I mean, how many of us, I suspect only a few of us, don't have workarounds that we've invented in our shacks. So, you know, it's kind of too bad we have to do this sort of thing, but that's the way it goes for the next satellite, and maybe we can improve things on the one following that. So let me add again, thanks for getting Foxtel M. Thanks for putting it on your Mac or your Linux box or anything else. That, you know, a Fox in the box, that data is just so important to AMSAT engineering, for engineering and at the commanding stations. So, yeah, there's no, oh, where did you go? There we go. So, yeah, this is not an amateur radio satellite launching. It's the next to the last space shuttle launch, which, and I took this picture. I was there at Kennedy Space Center. Space shuttle is just the coolest thing to see. Anyway, so thank you very much for listening. If you have any more questions about LDS or whole orbit data, feel free.
Any questions? Yeah, heads up first.
Given your ability to fill holes, is that going to be an automated process that your system will figure out what the holes are and then automatically set up, or do you have to manually make that command?
You have to manually make it. We don't really have any automatic uplink of any sort for our satellites.
So will this be a command station responsibility or an
Yes.
engineering station?
Well, I mean, to be honest, for Fox T, for Golf T, sorry, I think there's negotiation to be done between the ground stations and and engineering as to exactly who does what and when.
Do you want an answer now?
If
no,
you
I'm
like.
kidding. I'm kidding. I'm kidding. I was pondering the same thing, Barry. Thanks, Barnes. Always informative, and we know the value of whole orbit data. And those of you that haven't looked at some of the number, there are millions of frames of data that have been collected from the various Fox satellites. My question is it's sort of an old reflection that at one point, a couple of our birds did have a 9600 baud
Yeah.
mode. So why going forward aren't we doing something like that again?
I think the answer is that we knew how to do the 9600 baud with an FM transmitter. And to be honest, I never liked that mode because if you look on the spectrum analysis, it's splattered all over the place. So I think if anybody really paid attention, there might be some issues there. But I think the real answer is that we knew how to do it with FM. It takes up a huge bandwidth, so you know it's not going to work nearly as well in a linear transponder.
Any plans to ever run a file system so you can just ask for the file to be downloaded?
I'm glad you asked that. Mike is here to talk about Fox Plus, and there is some possibility of another Fox Plus having more packetized data. So I'll let Mike answer that question. Or I'll let Mike answer the question when he gives his talk.
Any more questions? All right. Burns, I just want to thank you for putting together the Fox in a Box thing. You made it so easy for people to set up home stations that there's no excuse why they don't.
Yeah, well, so I have to say that Alan contributed hugely, Chris contributed hugely to the Fox in the Box. But yes, it's easy to put together. Get one. If you have a Raspberry Pi, you can download the software for free. So do it.
Burns, I will say, it's so easy, even the AMSAT president can do it.
Yeah, that's right, you did, didn't you? How many calls did I get about that? Thank you.
Yeah. There's a certain button you hit to hit the presentation. I can't get it to come up. Oh, you got to do it through Google, I think. We'll do it that one there.
We'll do it that way. Okay.
All right, hi, my name's Kip Moravec. I'm going to spend the next 30 minutes talking about the electronic power subsystem, or EPS, for the Golf T satellite. I kind of find it hard to believe that I presented the concept for this at the 2022 AMSAT Symposium, and now the hardware is almost finished. But there's still a long ways to go with the software. So just a quick overview. The EPS is pretty simple in concept. We take power from the solar cells, charge the batteries, and provide power to the rest of the satellite when we can see the sun. When we can't see the sun, we run off battery power. If we need more power than the sun can provide at any time, we can also use the battery power for that to supplement the shortage for a short period of time. For low Earth orbit satellites, we go around the Earth about every 90 minutes. In the 5-year lifespan of the Golf T, that means about 29,000 charge-discharge cycles. Full charge and discharge of batteries normally kill a lithium battery in about 700 cycles. So we decided not to do that. And I'll talk more about that in the battery BMS system or section. The most we can get, the solar cells can produce about 35 watts maximum. That's the ideal conditions, and the solar cells pointing real perpendicular to the sun. We currently estimate that the electronics will use between 20 and 22 watts of power. I haven't seen any good breakdowns of that, or how much power per voltage, but we don't know how accurate that estimate is. So we probably won't know everything in details until we actually put everything together. So one of the things I did was I over-designed the power supplies. We're providing basically 3 different powers. 12 volts, I'm allowing up to 1 amp, 5.1 volts up to 6 amps, 3.3 volts up to 6 amps. As you can see, you add those up, that's way more than 20 watts. But one of the things, the larger the inductors, means the lower resistance. I use low forward voltage diodes. All this is so it'll run cooler, and that hopefully will make everything more reliable. And we can handle unexpected power differences down the road. The other problem is that, you know, it's hard to get rid of heat in space. You know, you just can't put a fan on a hot part like you can down on the Earth. Okay, this is a simplified EPS block diagram. It's pretty close to what I presented in 2022 with just a few changes. Power from the solar cells comes from the panels on the exterior of the satellite to a MUX. This MUX allows me to reroute the power in case one of my MPPT channels fail. The maximum power point tracking, or MPPT circuit, is designed to get the most power from the solar cells. In the ideal case, outputs are 19 volts to the power bus. There's a processor dedicated to the MPPT chips to help keep them working together and to provide power information to the system over the CAN bus. So this is more power in from the satellite or from the solar cells. Then the redundant 12, 5, or 5.1 and 3.3 volt power supplies provide power to all the rest of the systems on the satellite. There are 2 independent battery packs made of 4 18650 batteries in series. Each of these has its own charger and fuel gauge to show the state of the battery. Most of the chips are not radiation tolerant or hardened. The supervisor processor is radiant tolerant, and we'll check the rest of the system to reset parts that are not working correctly from a radiation or other kind of unexpected event. All systems report their status and telemetry information to the CAN bus, which goes to the IHU that Burns is working on, and provides a status of all of the systems. So this is how I broke up that into actual physical PCBs. Gonna take this over here. So this is the Golf T model. And if you look at it, this one is my battery board, which is the battery BMS PCB. This green one is the PDU PCB, which is the power distribution PCB. So that's got the 12 volt, the 5.1 volt power, and the 3.3. And then this blue one would be the MPP PCU PCB. And I've also, so that doesn't have much detail in them, but this is the battery board, the 3D model of it, which I'll pass around. This is the PDU, the white one, is the power distribution. So that's my least dense board. And then this is the one that's almost done. It should be, the other 2 boards are built, or are being built. This one, I knew I had a bad connector on here on the 3D model. I thought I fixed it, and then I sent them the wrong 3D model. So this one's got a too tall connector on it. Yes. Okay. So let's see. Did I miss anything? Okay. Let's just go through the boards. The MPPT PCU takes basically the power from the solar cells and puts it out at 19 volts to the power bus. The PDU takes the 19 volts and converts it to the 12 volts, the 5.1 volts, and the 3.3 volts for the rest of the thing. The battery BMS takes the 19 volts to charge the batteries, and then if there's any time that we can't provide enough power, like when we're going when it's dark out, the batteries will provide power to the power bus. Or when there's not enough power, the batteries will help power it up. And then the PDU can work all the way down to, the PDU boards can work all the way down to 10 volts. So we've got a lot of range. And so when all this is happening, the rest of the satellite doesn't see anything going on. Now, one of the changes I made from 2022 is placing processors on the PDU and on the battery BMS. What it did was it was simplified my connections between the boards, and then it made the boards also more modular. So I could work on just one board without having them without having the stack of them all together all the time. And then all the EPS processors, or all the processors on this thing, will spend most of their time asleep unless there's something to do. And they're basically, the yellow ones, the PDU, the BMS, and the MPP, they're basically state machines. So when there's something to do, they'll do it. When there's not something to do, they'll be sleeping. Because I don't want to use all the power on the processors for the EPS. Next one. So as we mentioned, and I'm passed around, 3 boards make up the EPS. That first, the MPP PCU is the maximum power point tracking power conditioning unit. It's the densest. That one is 8 PCB layers. The second, the PDU, is the least dense. It only has 4 layers. And then the third, the battery BMS, is in between on the density with 6 layers. And that's because it's got those batteries on side, but I have to pack all the electronics really, really tight in between the batteries. So while it's not dense all the way across, there's certain places it has to be dense. And one of the reasons we have so many layers is that I have to have a ground plane next to the outer layers. What that does is it lowers my emitted radiation from the high frequency switching, because power supplies are nothing but high frequency switching. And so that will help our RF receivers not have a lot of noise. Okay, we're using these, the stack of the PCBs have to have a connector between them, and we've chosen the Samtec, they're QSH and QTH, 60-pin connectors. They're small, as you can see on the board. They're really small. They have a pitch of about 0.5 millimeter, or 19.7 mils. And the QTH part is available in different heights. As you can see, I accidentally got that one the wrong one. But the footprint's the same. And like the battery BMS has a real tall one because those batteries are real, real tall. Each pin on this thing can handle about 2 amps, while most of our connections are less than 10 milliamps range because they're signals. But we use multiple pins for power. The power bus uses 5 pins. The 5.1 volt power uses 4 pins. 12 and 3.3 use 2 pins each. The connector has 4 additional separate ground pins other than the 60. They're right in the middle of the connector, and they can handle up to 25 amps total. So that's for the ground, connecting the grounds between the boards. And then currently in our design, we have about 8 of them that are unused, that we can use for future expansion. So I'm going to go next with the block diagram of the battery BMS. And like I said before, there's four batteries in series in each of those battery packs. Each one has a fuel gauge, each one has a charger. And we're using the TI BQ40 Z50 fuel gauge chip. And the chargers, what TI did was they built the fuel gauge to actually be able to control the charger. But to do that, the charger has a fixed I2C address. So because they never assumed people would have more than one on a board. And so now I have to have, so in this case, I have to have 2 different I2C buses, one for one set, one for the other set. Fortunately, the processor has, I think it's 3 or 4 I2C buses, so we're good for that. So the other thing is the charger, or the fuel cell, wants to, when it automatically sets the charger, it's trying to charge as fast as possible. Well, our problem is that we have to take into account what's going on in the rest of the system. So we may have to say, okay, we can't charge full throttle. We may have, because the rest of the system is using power, we have to use what's left to charge the batteries. And so the processor will get in that loop and tell the charger how fast to process based on how much power we got coming in and how much power we've got going out to the rest of the system. That delta is what I've got to charge the batteries. Okay, this lithium batteries, they advertise how many times they charge, and usually it's in the 500 to 700 cycles. And as I mentioned earlier, our 5-year mission is 29,000 cycles. That's a problem. Fortunately, when they talk about the 700 or 500 to 700, they're talking about full charge to full discharge. When I did my calculations, it looks like we're only using 20% of our battery. So during the dark side, when we're dark. So if we charge the battery to like only 80%, when we discharge it, it'll go down to 60%. So we're not using that. And that dramatically increases the number of charge cycles. So what we're going to do is, unfortunately, I haven't seen any good numbers on exactly how much that does, or how much it increases. I've just been told a lot. So the next thing I've started looking at is, well, what happens if we only charge it to 60%? Well, when we use 20%, we discharge to 40%. But now we're closer to that 50%. It was, when you want to store a lithium battery, you store it at 50% charge. And it'll stay, it'll last almost forever at 50% charge. So what we're looking at is trying to lower it down as much as we can and just work in that smaller range around 50%. I would like to do some testing on this, and but it just means, and now that I moved to Michigan and I have a better workshop, I'm probably going to do some of those kind of testing on how to do, or how many cycles can we actually get, and what parameters do we need to set to get us way, way, way more. The other thing is that the packs are completely independent of each other. So if one pack dies, the other pack can still be working. And then if all else fails, if all of the batteries die, then we're running just when it's light out. When it's dark, the satellite shuts down and then wakes up again when we're back in sun. This is a battery BCB layout. You may not have noticed, but the batteries are offset a little, and that's because the tabs go through the battery. And that's what these are. So these two are together, and these two are together. They're on different sides of the board. And then I've made the independent part of it. Basically, one side of the board is one battery BMS. The other side of the board is the other set. So that kind of made the layout a little easier. And like I said, this is a 6-layer PCB. I don't want to screw this up. There we go. Maybe. Nope. There we go. All right. Next slide. Okay, wrong direction. Okay, the next one is the PCU block diagram. And again, all I really was trying to show here is that the power bus gives us the 10 to 19 volts. This board converts to the 3 different powers. Each power supply is redundant. So you can see there's 2 12 volts, there's 2 5.1s, there's 2 3.3. And then I feed them both into one filter. Filters all passive parts, so I'm not as worried about that working. Normally one will be on, one will be off. I'm also going to look at one of the other things they do in server power supplies is if they have dual power supplies, they run one just a little bit lower voltage than the other. So in case one fails, the other one's already on and can pick it up. So I haven't decided whether we're going to do that or not, but we'll figure that out. But it'll work either way. I've also, with high frequency switching, there's a lot of RF noise, and that's why I've got the wideband filters on each of the outputs, so that doesn't translate through the power lines. I mentioned earlier that I've got a ground plane under each the top and the bottom layer to help minimize emitted radiation. And the high current paths in the power supply have very wide traces. They're basically copper pores, again, to minimize the EMI. And then finally, we can control the switching edges to reduce the higher frequency components of the square wave. All right. And that's the front and the back. Pretty much that one corner, that upper quadrant, that upper right quadrant of the yellow one is empty. I've got some traces going through there, but there's no parts on it. So I've got room for EPS expansion on this board. And this is, like I said, this is my least dense, so this one's only 4 layers. Now comes the problem child. So this one is my most dense board. There's 4 independent MPPT chips one for each set of the solar cells. So what they've done is we've broken the solar cells into 4 parts. There's the wings have their own MPP, even though it's 2 sets of solar panels. The very front one and the very back one have their own. The mucks, I can change those around a little bit. And so, for instance, if one of my MPPs go, then I'll probably switch off the one for the back and use the 3, switch it out with that one handling one of the front ones. Now the TI has a BQ 2575 6R MPPT chip. It's actually designed as a charger for charging a battery with solar cells, but I've talked to them. They've said that yes, you can use that as a power supply, and so what we're doing is it's basically like treating the rest of our system like it's a 19-volt battery, and so we're just doing that. They recommend 1,000 microfarad capacitor on the output, so the voltage doesn't sag too much when they stop switching to check the output. Well, that I can't do. The problem is that I don't have enough room for a ceramic 1,000 microfarad capacitor on my boards. And you can't use electrolytic because they can't go in space. They'll blow up. So what we're hoping, or what we're expecting is going to happen, is that the other 3 will help hold that one up so that none of them are really sagging when they're doing their checking. So we have probably about 100 microfarads on each of those, but we can't do 1,000. So we're expecting that that's gonna that'll work in there because we got 4 of them running instead of just 1. I had to switch my processor for the MPPT to STM32G474, and it's the one that'll be checking everybody and making sure everything's working right. This board also has its own 3.3 volt power supply, independent of the PDU one, because I have to be able to bring this board up first before I can get the 3 volt power supply for the rest of the satellite. And it can pull power directly from the PCBs or from the solar cells before it goes to the MPPT. I've also put a 2.5 volt and a 8 megahertz references on here so that they do go to the other boards. So everybody has the same clock reference and everybody has the same voltage reference. So when one board's trying to measure a voltage and another board's measuring the same voltage, they're actually reading the same because the reference is the same. It's not like everybody has different references. And then the supervisor is a radiant tolerant TMS 370 LS 0914. That is the same as what's used in the RT IHU, and we did that on purpose because it is radiation tolerant, and we have software, and and it will monitor the other processors in the system to make sure that they're running. If they're not, it can reboot them and recycle them. And then this is the front and the back. This isn't, oh, I forgot to mention, there's 4 connectors on this that go to the panels on the sides of the thing to get me my power from my solar panels. And there's also some other signals that are passed through this thing. I tried to do this board with 6 layers, couldn't do it, so I had to go to 8 layers. The 2nd and 7th layers, again, are ground planes, and the 4 inner layers are just purely connections. The PCB images are not the final design. I still have to go in and put in copper pores. Like you saw on the other one, it looked like it was full of copper. That's what this is going to be like too. That's also going to help me with my RF radiation. Boom. The battery BMS and PCU assemblies have been released for production. We've been getting quotes to have them built, but I don't know yet if the build has been started. Yes? Okay. The MPP PCU still needs copper pores. I'm going through the BOM to verify all the parts are correct, double checking all the components. I've got, I'm hoping to release that one by the end of the month. And finally, my requests. I'm going to need help with software. I have 3 boards with 4 processors that need programming. I can't do them all at the same time, and I really need to be concentrating on the MPPT board. The other boards are fairly simple. And then my biggest concern was the TMS 370 LS 094, as I have no experience programming that one, and I'd like to have somebody pick up. I think Nick is thinking about doing that, and I'll be very, very happy if he can pick that up. The 3 STM processors I have code working on the lowest ones because I use that one all the time. So we can talk on the serial ports and the I2C ports and the others. So that's going to give us a lot of help. Thank you for letting me do this. Do we have questions? I got a flag that says we have less than 5 minutes, so I don't have a lot of questions. Right there.
Really, really cool designs. I have several questions, but I'll get to over lunch, I guess. So,
okay.
But based on experience with about 20 systems like this and their failure modes, I2C buses are known to latch up, and when they do, they latch in a high current state, and they can only be cleared by power cycling the devices at both ends.
That's correct. And we've got that in there.
You can accommodate
Burns has informed me about that, and we took care of that.
Cool. Thank you.
When you're pointing in the sun, what's the temperature rise on the panels?
I don't know.
And how about the rest of the sunlight getting really cold?
That's good. The power supply generates heat as a general rule, and we want to try to minimize that amount of heat. But from what I've been told, the batteries are not going to get really cold because of that self-generated heat and the heat from the solar panels. What were we, Burns? You were looking at that data on other equipment.
Well, yeah, that's different because the one used the word
Yeah.
flat panel.
So yeah,
I mean in general, not very much, not very cold.
Yeah, it's not getting very cold.
Jim, and anybody else, if you have more questions, I plan to allow questions to any of the engineers during my piece this afternoon. So feel free to jump in then. Don't let them slide by, or I really hate point to point, because then only you know what you're talking about. So we'll do it this afternoon. Thank you.
All right, I think we're done.
Yep, thank you, Kip.
Yep.
Okay, guess what? It's lunchtime. So we will break, 1 o'clock, start back up with Golf Tee and Fox Plus updates from our engineering team. Thank you very much. restroom if we get some toilet paper, paper towel. Yeah, yeah, I'll stall. All right, everybody get a good lunch? Okay, we're getting in the final stretch here for this year's symposium. We're going to close out the early part of the afternoon with an update from AMSAT Engineering. Mr. Jerry Buxton is going to talk about Golf Tee, and Mike Moore is going to talk about Fox Plus, and together they're going to talk about everything else. Jerry stepped out for a second, so let's see. Have y'all heard the joke about two AMSAT volunteer engineers who went to a bar? Me either. You come up with a punchline for that, then maybe we can get something started. Yeah. This evening at the banquet is going to be right in the same room here. So after we finish up the general meeting, the hotel staff is going to come transition this into a ballroom. Everybody's name, it looks like, well, I say that. Usually when I look at people's name tags, it says raffle ticket name. But that name is where you're supposed to write your name on. So make sure before the banquet tonight that you take a moment, share a pen or whatever, write your name on there so when it goes into the bucket that name doesn't win, that actually you do. And then other than that, we've got, let's see, so at about 3 o'clock, Drew will come on board and hold the AMSAT annual general meeting. And we'll get to hear something from our new illustrious president of AMSAT. Oh. Okay, Jerry, hopefully he comes back soon. I've run out of stuff today. Yeah, I know where he's at. So, when you get older, you got to take more trips to the men's room. What? Okay, Jerry, they didn't really come here to see me, so.
That's okay. I'm working my way up here.
Yeah, there you go.
I'm going to steal a line from somebody else. And I've got terminal sinuses, so I didn't want to start sounding like a froggy, drippy guy. Is audio okay? And clicker? Click. Nope. You got to point it? Let's see. How about that way? Anybody done this before? You know what? There. That's what it did.
Okay, doesn't work.
But we do build satellites. I just wanted to start out with a recap of all the presentations that have been done here. And for people watching, either at home or on the recording, Cameron Castillo talking about our propulsion program, Andrew Robinson about mechanical, Hamir Sverson, I got that wrong, didn't I? The Golf Command and Control, Burns Fisher talked twice for the Golf Fox Plus telemetry and the whole orbit algorithm. And Kip Moravik was last there up there with the EPS. And I don't know if you noticed, but there's a lot of talent we've got working for us, and that's only a part of it. But thank everybody who did come to present engineering stuff, if you will, because it's a great way, a great outlet for us. People are always looking for engineering updates, and pretty much I'd mumble something and they misquote me. So it's a whole lot better just coming from the people doing it. And like I said, there's many more. So we've got a lot of hard work that go into these projects. They're behind the scenes, I guess you'd say. But if you consider what it takes to do it, they've shown you here, for example, in your lifetime, spare time, hobby time, you got family, kids, dogs, job, and all that kind of stuff, not to mention natural disasters and such. So it takes a while, but we built some really solid stuff. That's the thing. And in that, Didn't mention it on that slide, but I mentioned just before the break that if you have more questions for any of these engineers who are talking up here, you'll have a chance to ask them. Because I know there's probably a lot of questions, and some of them come to you, after you have a full belly or whatever. I'm just going to start with talking about the golf program, and then I'll pass it over to Mike to talk about Fox, and then come back to kind of end it with what we're doing in AMSAT. So Golf T and Golf 1, these are two satellites that had been CSLI selected. They're part of what we call the golf program because the intention is to have more than the two. Golf T is the technology, and I can't remember what I called it. Technology exploration environment, that's it. And Golf 1 then actually kind of goes back to our normal way of making satellites. And like I said, we'll get down to Ascent with the SDRB. Too bad Ray couldn't be here, but you've probably seen it in the ads as SDR Gen 2, I believe. Microwave ground station, Jonathan and propulsion, some guys, right? That was a neat demo they did. Some of them have asked, maybe all of them, that if you want to help with what they're talking about, please talk to us here. Even if you just want to inquire, and maybe nothing comes of it, but we need volunteers. And for the work that we need to be done, at least in these areas, there's no better chance for us to find out and for you to find out if you can help out. A lot of them are one-man jobs, or one-woman jobs, of course. And so that's another part of why it takes so long. We've got to devote ourselves to different aspects even within the project that you're working on. So we do need your help. Talk to people at home that are watching. Same thing for you. And you can reach out through, Frank, correct me if I'm wrong, email to help@amsat.org. Volunteer@amsat.org. Don't believe what it says on the slide. So email volunteer, volunteer@amsat.org, and just mention the project or the person, project and person would help a lot. And we'll get those emails and we can distribute them and actually hook you up to talk so that, as here, we can find out and you can find out if it's what you want to do. Golf T satellite. This is progress, changes, etc. Over the last year, basically, the purpose to develop and test our own design of deployable solar panels. Pardon me. Taking a lot of power, Kip talked about this a bit ago, to run a satellite that does any fun stuff, and that means a lot of solar panels, and they can be very expensive, especially for deployable things and things you can point at the sun. Now, the ones we're doing are fixed. They will flop out, if you will, and you've seen. So we have to point them at the sun with the satellite, but it appears that they will give us the power we need to make it work, and that's what Golf T is all about. They want to test that to see if that design works and if that design provides the power we need at the level we're thinking. We can add more panels to that, so each panel could deploy 3, sorry for the P, they could deploy 3. Can you hear me if I'm here?
Yeah.
Thank you. Say again?
You're 5'9".
Thank you. I just don't want to pop P's there. Yeah, so we want to find out we can expand it, put a third panel on each side, for example, if it's good, and that'll give us more power from a Golf 1, perhaps. For example, we've got a commercial, and it was always intended to be a commercial ADCS. Our first vendor, I think there's a little story about that later, but we're not flying the first one that we partnered with. They were a new startup, and so that gave them an opportunity to go to space and us an opportunity to get a cheap ADCS. We have our in-house designed RT-IHU, the radiation tolerant IHU, which was a Ascent project idea, and during the Fox years, as the IHU, although it was designed to be able to reset and recover, did reset hundreds of times, right? And I don't know if that heat map is still good of where all the resets were, but most of them were in the South Atlantic anomaly until it got older in life, and then they started having more random places. So the Timeout. All right, sorry. I'm trying to hurry because I think I started late there. The RTIHU is flying against the LIHU, the legacy IHU on Golf T, because we know that the LTM, the legacy IHU, the improved command receiver, the transponder have flown before and are highly likely to work okay on Golf, in case RTIHU does not. So LIHU kind of watch over it, and if it works as good as we hope, it just won't have the resets that we do. Unscrews? Oh. Thank you. Same level? Okay. Where was I? Oh. You want to knock it up a notch there a little bit so I don't have to get too close? Hello? Well, all right. Well, I'll modulate it myself. The RTIHU. It's supposed to not have so many upsets. Flying against the LIHU, it also gives us an opportunity to test how a Fox 1, which we know how it behaved in a LEO as far as those upsets in the South Atlantic anomaly, and compare to that, and then the 10 gigahertz SDR is part of a high-speed telemetry and beacon test. It is high-speed telemetry at LEO on 10 gigahertz. It's not like we're expecting everybody to be able to capture anything, but the idea is to prove the concept that we can do it, among other things, and is intended for the higher orbits where we have higher gain antennas, slower passes, and such like that to be able to relay. Some years ago at CubeSat Developers Workshop, we had a lot of success with the Vanderbilt experiments on the Fox, and Burns mentioned the data under voice telemetry. And some of the universities were curious about flying experiments, and they asked me if we could do any higher data rates. They wanted like a megabit is probably slow on what they would want now, but so that's why this was put in here as an experiment. That was back in 2017. It wouldn't have done any good to scale it up right now because we're going to be pushing it just to test it. And all of these then must be flown as soon as possible. So it's kind of a tricky balance. It's so easy to get into pushing for perfection, to make everything work right because you want it to work, and that's how we build these things. But there are risks that we will have to take. And the idea is we want to know if the deployable panels work, if we can run an ADCS, THU, and the microwave works. That's all we need to do is prove that. It could, literally be up there for a day, but we don't want that. It does have built-in fallback. Because of the LTM, LIHU, it will do the dummy transponder, if you will. If all else dies, you can still use it, assuming battery or solar power. So, yeah, if these things all don't work too good, then the idea is we build ham radios in space, and we want one. So, there you go. The scheduled drivers for Golf T. I think I mentioned we had a launch at one time. In 2017, we found out the opportunity for these. It was approved by the board. I wrote the 2 CSLI. In 2018, February, I believe, we were accepted. And, bless you, going through at a more or less typical pace. So in 2021, we were offered and manifested on a USSF launch. STP for their test program, S28B, Sierra 28B. It turned out that we were unable to do that because the vendor who was making that first ADCS did not deliver in time for us to keep up with the timeline for that launch. So we were able to back out of that. That's something you don't really want to do when you get a launch. You know, NASA's going to pay for our launch, and you don't want to not show up. That's kind of not good faith, at least, right? Fortunately, it really kind of wasn't AMSAT's fault. They said, hang it on Ragnarok and try again. So that's followed immediately, practically, by the death of Bob Davis, our mechanical engineer at the time. I think I've mentioned that he had been with AMSAT since he got out of college, I believe, and doing mechanical engineering, and he knew a whole bunch about any of the satellites we'd built. So he was a great resource and also a very good mechanical engineer. With his loss, because we're pretty much, like I said, one man per project type of thing, we went and found some good new mechanical engineers, and that would be Tom Kronauskas, related to the guy back there in the corner running the show, and Dwayne, what was Dwayne's last name? Dwayne Moberg. Dwayne Moberg is working on the solar panels array, that part of it, and Tom is building the space frame, and which is quite a trick. You saw what was inside, and I'll show you some slides on that. But they were, and you know, they're great mechanical engineers, but they're just totally new to the way, at least to the way we build satellites, which is, you know, it's all homebrew. So, but we're making. It took a while to get them up to speed, but they're kicking butt now. So, and then of course the third thing that's a schedule driver or HINC would be the complexity, because as Burns, I believe, said it, this is 3 times the volume of Fox 1. It's a 3U versus a 1U. It's 90 times as complicated. And I think I started that with 30 times as complicated just because it was a carryover of the 3, right? And we wound up upping that every so often. And what makes it goes in there that's so complicated, first of all, it's a first design. Fox 1, ultimately Fox 1A, was the first CubeSat AMSAT had built. And so that was the first design at trying to fit a bunch of stuff into a very tiny volume that, you know, was preceded almost, if you skip over AeroSat a little bit there, but, you know, AO40 was huge. And a lot of stuff to work with, a lot of place to put antennas. Fox is amazingly dense with capability, but that's what we're growing from. And to take that same idea that took about 7 years, I think maybe, to get to a launch, we were, in 2021, pushing 5 years maybe, which is pretty darn good. But it is still growing in the amount of the complexity that we encounter. So brand new design, you got to expect it's going to take a while, but it's going to be a very, very good design. Here's what I promised about the look inside. And this is a picture of, last year of the model that we had. So I think the colors might have changed in the model that's here. I'm not certain, but they're still in the same position, basically. You got, on the top there, your ADCS. This is going to be provided by or purchased from CubeSpace, which is a South African company. And they have made, and I believe flown, Burns, yeah? They've flown a few? Yeah, lots, okay. So they've made and flown lots. What we're able to get from them, the package is scalable as far as the size of momentum wheels and the sensors even, magnetorquers, and whether or not you need star trackers and such. So the pointing accuracy for Golf T is a couple degrees, I think, couple 3 maybe. And everybody seems to want better, so they were a little bit surprised by taking it at its bare bones. But we're just trying to point the patch antenna toward Earth or the panels toward Sun, and a couple degrees won't make a difference to us on this mission anyway. You got your magnetometer for that sitting on the top there. The magnetometer does the magnetic field measurements, such as Burns was talking about in the telemetry. And I guess I had that blocked together before, but that's the CubeSpace, Cube ADCS there. Cube Computer is the interface to our bus to talk back and forth between their ADCS and our IHU. And then our CIU. CIU is the Common Interface Unit, and it is a board, a matrix of different connections and cross-wiring and also controls to route all the wires that have to run, that don't run in the bus. You have to run wires externally to the solar panels, for example, and we have to have some wires to the, a bus to the ADCS. And so that handles all that. Also, it's involved in the separation switches, the safety RBF pin separation switches to keep the satellite unpowered while it's in the dispenser and getting ready for launch. The maximum power point tracking. That's a pretty good one. So this is what Kip addressed. I think it's got in little bits the MPPT here, and so this is not BMS. No, that was PDU. Sorry, that was a test. Thank you. You're awake. That's what matters. Now, so the battery, yeah, the PDU, power distribution unit, and then the batteries down here. And there you go. How many we got in there?
8 batteries.
Thank you. I wanted to verify it, right? Because I think I wrote 6 on the NASA report or something. So yeah, we have 8 of the 18650 cells. And what are they, 3600 milliamp or something like that? What's their capacity?
Oh, I don't remember.
Don't remember. I think I remember that number from the wrong number I put on the NASA report. The 10 gigahertz SSPA. This is a bit of a trick, but the point of this in the picture is that it is heat sinked to the frame. We have some special metal around it, if you will, so that it can have contact with the frame there. And there we go. That's a sun sensor. We have coarse and fine sun sensors that could go everywhere, but when we were designing this, we didn't have that many everywhere to put it. So we do have it covered as far as what's required or necessary. And so there are other places, but it's not shown on here. The orbit grade GPS. In other words, this is one that will let you record high altitudes and fast speeds as in orbit. And that's connected with, it is not required by anything specifically, but it helps augment the ADCS to keep it updated on where it is, so it makes sure it's doing what it's supposed to. And it also provides use for us. It provides a clock, and that's all I can think of right now. So that is something that is mounted kind of weird to this. We call it the ADCS piggybackers. It's because if you look, it'll be on the next slide, but in this stack, which we call the transverse stack because it's not up and down like we like them, this is our standard avionics stack and bus. So it's got the LTM in it, Vanderbilt experiment card, and something else. Anyways, I'm going to turn it sideways here. Oh, and then there's room downstairs, if you will. Golf 1 is intended to carry a camera for a high school student experiment. It's been a long time since we, hooked that up, so I don't know, they're probably graduated and waiting to do their job like this or something. But we plan to fly in some kind of camera experiment for students for STEM. And then also right now, it will be housing the Earth Horizon sensor for the ADCS. It needs to look out at an angle so that it can make sure that it can discern the Earth from any other brighter source. And so it was kind of something else to try to wiggle in there because of the way it's designed and the angle it has to peek out the side. So one of those complex challenges. The 10 gigahertz patch array antenna by Kent Britton is on the bottom. I'm not sure I have a picture of it. It's a 4-patch antenna, for 10 gigahertz. It's very broad beam width because in case we can't point it directly down, we can still, still use it. It actually works out that if it's, say, pointing down at you as it goes over, you can still work people off to the edge of the footprint because they can get into the sides. Kent says it's even got higher gain out there, so it gives the opportunity for the 10 gigahertz signal not to just kind of go swooping by, but be able to be heard throughout the pass more or less. The SSPA is, I mentioned it, enclosed for shielding there. Both RF EMI as well as then the heatsink. The EDIS E310. This is why we have a transverse stack, because we had the EDIS E310 radio, and we were expecting that we could modify it to be able to fit our 4x4 board footprint, if you will. And we found out early on that they wouldn't let us do that. So the only alternative, because at that time we were just into the CSLI, so we were pressing to move ahead to make that work. And so it is mounted. And you can see it's just longer than the other boards. And so that's the cause for the transverse stack. That will change when we get down to that SDR-B, or the SDR Generation 2 is expected to be able to fit in there for hopefully Golf 1, and it's coming along pretty well. Vanderbilt ISDE experiment is stuck on the end of this. That's one of their radiation experiments where they look for upsets to various types of RAM and into even, what do they call it, like the 3D RAM that they use in GPUs and graphics and stuff like that, but I forgot what it's called because it's been years. But that's what they're going to be looking against. They look and see how many upsets they get, how when the pattern changes in the low Earth orbit. So that gives us also a little insight as to what the radiation is like over SAA, for example, where we're expecting to see RTIHU behave better. We got the fixed solar cell panels, and Kip went into this too about the MPPT, but the front and back, if you will, have fixed solar panels. I think the back one's down to only 6 instead of 7 cells because we needed more room to plug stuff in. And they got the RBF pin battery charge connection, umbilical connection, and some warning indicators there, and that's pretty much on or right next to the CIU. The active warning indicators are simply for ground use. If the satellite becomes active, you want to know it before it unleashes antennas or solar panels or something. And a little look at the solar panels as they deploy. You can see it again on the model there, but I thought bigger picture on the screen might be helpful. So let's talk about that schedule. It is, you see the top purple circle up there? That's where we expect to have the full EM in a stack, basically, a satellite put together. Probably sans solar cells, of course, but to do the engineering model testing. And that's commencing just after the first of the year. Once we get along through that, about the end of March, hopefully everything's happy. Down at the bottom is the milestone for the CDR, the Critical Design Review, showing March 3rd, beginning of March in there, although that overlaps a little bit with the engineering model testing, so things have been sliding for quite some time. Then after that would be the flight model build and testing, with the expected delivery to come, well, call it a handover readiness date. We'd be able to deliver it and integrate it for a launch on, actually, we were shooting for September 30, 26, but I'm kind of thinking that we're probably gonna, because we have to look for a launch, we don't have the CSLI and such like that, that I'm gonna call it fourth quarter. So by the end, by December of 2026. And I have pretty good confidence about right now. CDR, of course, will either make me happier or knock me down. Now, so with the CSLI no longer available, we're looking at the need to, or if we want to, and we decided we did, to purchase a launch. So it's about $300,000 for a 3U to LEO, and that's what NASA includes or as the cap on their grant. It's really a grant to pay for the launch. And so I think that the commercial price for that, I'm certain you can shop around and find something less, but yeah, that's the value of what the CSLI provides us. And the current project schedule with the CDR in March does actually allow the time for us to wait until CDR, which I would anyway, before I purchase a launch, and see if CSLI is revived in whole or in part, because they're planning on having a review of the fact that they had to make the cuts in March. And so, being an optimist, you never know. I'm going to hang out and look for that. Yep, and there's that December 2026 date. So, Golf 1, there's not a lot to say about it right now. It's always intended to be about a year behind Golf T. We want to learn lessons from Golf T, and at the very minimum, it was learning as we construct it what works or doesn't work, what can we improve in the construction and design process, and it also gives us that opportunity to grow our skills and capabilities for making deployable solar panels, for example, and all the fun new complex stuff that's involved with it. It further establishes the microwave band usage. Now that's really important, pardon me, because the microwaves are where we have to go. First of all, we chose, and I recommended that we do the 5 and dime back when we had the CubeQuest challenge that we were providing communications package for. That would have been a lunar orbiter. And also the Phase 4B, which was going to be a GEO satellite that originally started out as being 3 and 5, I think, up 3, down 5. And I talked Bob McGuire into making it 5 and dime so that we have a kind of a compatible standard across several new satellites so that the users don't have to have a different kind of radio or more equipment in order to be able to talk to these things. By doing that, with the 10 gigahertz down, 5 gigahertz up, and then you've got 2.5 that will be on the satellite in order for the QL100 users to be able to use the thing without having to change their equipment. And the more that we populate that upper microwave stuff, first of all, it's too crowded below. It's just a fact. VHF, UHF, forget it. And especially when we get far away, which we will, you need to have smaller antennas, bigger gain, and the opportunity to fit that on a CubeSat. So it is the unavoidable future, I'd say. But we have, there's opportunities. We don't intend to leave anybody behind to move into the microwave RF field, I guess you could say. The ham radio microwave, the 10 gigahertz beacon, that's part of it. Because with Golf T, we have a little pickoff for the SDR to be able to see the 70 centimeter downlink of the LTM. And it's going to repeat that down on 10 gigahertz. So that passband, that downlink, will be available that you could work theoretically, VHF up and X-band down. That just gives an opportunity for people to get some 10 gigahertz equipment, try it out. And we're also working on a ground station in order to give you a leg up on what you can use, buy, or build. Also, the microwave, I understand, puts us in a grant, position us for a grant for opportunities for launches and such, for higher satellites, because of microwave, as well as all of them, while I'm here, will carry STEM experiments, educational stuff, if you will, because that's the future. So anything we carry that helps high schools, universities, middle schools, whatever. If the kids got a chance to build a board instead of a whole satellite and fly it and get some science, how can you lose? Well, I just said that, didn't I? And Yeah, this was, since it had a CSLI, if CSLI resumes, we are back into the field of that. Now, Golf 1 was never going to go, well, it was intended to go to around 1,200 kilometers, because that's up there with AO29, AO7, and I thought, hey, you know, since we're working our way back to HEO, the whole Golf idea, if we had something up there, then, you know, maybe if one of those fails or something, we can help, so to speak. And it also begins to stretch the capability for the microwave and such. Unfortunately, of course, yeah, the orbital debris rules changed, and especially the orbit lifetime down to 5 years. So that squelched that. What really killed it was the fact that there are no, or were no, commercial means for us to get back down if we went there. There was nothing that had been used or approved for CubeSats. So despite the fact that there were ideas there, nothing had the 90% reliability, I believe, that NASA liked to say. And we couldn't fly 10 satellites to make sure 9 out of 10 of them worked, right? So nonetheless, all of this work we're doing continues to attract new and younger engineers. And you've seen that, you know, I'm one of them now, but like, you know, AMSAT was a bunch of old men for a little while, and it's just the way cycles go, right? Like your ham club or something. But we've got a lot of younger people getting interested in it, and it's great because it's the future for us. We can sit back and work satellites all the time, and they have new ideas, better ways to do things, different ways to do things. And the keen thing about that is that that's what other kids, younger people, are going to get into. And if you're a diehard old guy, you're going to figure it out too, because you like to do that stuff, right? So, you know, it's a great position to have younger kids designing, building, and taking over. I think that that's all I have here for golf. Fox Plus up next, but at this point, if you have any questions for me, or as I mentioned earlier, if you have any questions for any of the engineers who were speaking previously, especially about anything that was golf related, if you could make a distinction, but let's do that. It'll take a little time right here. What time is it? You can go with 1:40, so I got like 15 minutes left. Right, I started at 1, okay. So yeah, 10 minutes of questions. Anybody got a microphone? Thanks. Hang on.
My question is about the lithium cells. I noticed it's lithium ion and the 18650s I'm talking about, rather than lithium iron phosphate. What is the reason for that?
See, I cannot answer that. I don't know that. Our battery guy,
Yeah.
if you will, he's not here, so we could find that out. Any of our other engineers remember what was said about that, or if anything? 18650s have been on our mind ever since back in 2017, I guess. And the way that Doug is working with all this stuff, he works in the automotive battery industry, if you will. So is that, well, we would want it that way, and of course range safety and everybody wants it that way. But we don't see any problems with the way that they're used. But if you think there's something we don't know, I'd sure like to hear it, because that's where, you know, that's how you correct things, right? Other people looking.
Yeah, I've been dealing with lithium cells for, I just finished kind of a 14-year, let's call it experience, because I was retired and not a study, using lithium iron phosphate in an electric car that I built. And so I installed 48 lithium cells in 2011, and after 5,000 cycles, the cells were down to 75%. I replaced them at that point. So they're lithium iron phosphate. And another reason they're chosen is because they don't catch fire, and it's a good safety concern. Basically, the iron grabbing up all the oxygen molecules, and so it doesn't really support flame. And I don't know how that works in space, but the thing was that another reason for the choice was the number of charge cycles. And in that presentation, it said, well, we got this enormous number of charge cycles, and trying to predict the number of charge cycles. And during this 14 years, I've talked to a lot of researchers who were working on behalf of the automotive industry, trying to come up with how do you predict the lifetime of lithium cells. And there's no equation. Engineers, give us an equation and we'll figure this out. Product lifetime. And so and then when I saw lithium ion, I thought, well, they don't get as many charge cycles. So what was the priority here? And I'm sure, it was carefully chosen, but that's why a question popped up in my mind from my own experience.
That's, I'm going to, the cell number and such on here is not as new as what I misstated in the NASA report I was talking about. That's where I did find out the specific cells from Orbitron and model number and such like that. So there may be something in there. I've got it on my PC, that report is sent. So I'll take a look at that and see if it says anything different. And the lithium iron, you got LiPo, right? And then what's the lithium iron?
And lithium iron phosphate.
Yeah, but is there the abbreviation? I mean, do you call them?
LiFePO4.
LiFePO?
LiFePO4, yeah.
Yeah, okay. And I've heard that. I just wanted to make sure. So, yeah, I can check that. I can at least check out exactly what it is because I just ordered them. So that was cool. Yep.
Really quick, I've flown 40 satellites with NICADs.
Yeah.
You can't hurt them. They will charge and discharge forever. Why not NICADs?
We flew NICADs on Fox because at a minimum that I know of, because I joined, after that program actually started, but there was no information, no data on lithium, how much they could take as far as cycles and such like that. We flew A cells. It was designed for A cells to hold 6 A cells. And we sourced them through what was then, I think, Batteries America. Everett, don't recall his last name. But he actually went and found some and matched sets. He made us 5 matched sets, which was really cool. That's part of why we got 5 satellites out of it. And he said at that time that after that he would not be able to source any more reliable, non-junk consumer NICADs, at least in that size. So that's part of the reason we drifted away. We went away from that because of that, but also the expertise that we have with us as far as doing the lithium, which honestly, it was kind of funny because on the Fox 1 launch, I confused the range safety that, by saying that we have these NICAD cells, and they made me short one out and blow it up to prove that it wouldn't blow up, which it didn't, but it sure gave us a jump. So it's like they didn't even know what a NICAD was or something, But we went to lithium because it's just, we could not find any suitable NICADs anymore that weren't junk.
Don't forget that all of our satellites with NICADs failed because of batteries.
Well, that's true, but it fails because we mistreated them. Yeah. We ran those things full bore their whole life, basically. So, and I guess you could say that's my fault because I knew Tony Montero, my predecessor, had preached 20% discharge cycle, and I'm dumb, I guess. So I didn't realize that we were exceeding that until they all died, and then I went, maybe that was it.
For Golf One,
hey, dude, yeah, I got you.
For Golf One, are you considering a 1,200 kilometer circular orbit, or is it a more elliptical orbit?
I'm dreaming about a 1,200 kilometer. We won't get that.
You won't
because
get
we
that.
can't come back. Yeah, that launch opportunity offer came and went, probably 2019, I think. Yeah, it might have been 20 or so. It was just before COVID, I know that, I remember that much. So, we're not seeking that now, and with the current CSLI, our mission, mission manager, thank you. Mission manager, NASA, one of which was Liam, had suggested you're not gonna get above like 550 or so anymore. So I settled for that. It's like, well, you know, that's it. Because even then, that stuff was starting to come to market just in the last couple of years for CubeSats. And so, but that was too late to take an opportunity for that. I didn't not say it might not come along if they reawaken it, you know, with CSLI, that would be great. We'll go. If we can stick something on it that's suitable. Heck yes, I'd go. You know, that's like, but we can't, so the whole point is we're gonna use it to still learn ADCS and the control of the satellite pointing, power, and also we have that propulsion team that hopefully you saw their stuff yesterday. And in LEO, some opportunities to test that out, because I know if we flew a satellite to HEO right now, we'd be using commercial propulsion and probably commercial a lot of stuff, because we just don't know how to make that work. You don't want to run into everybody, and I call it Starlink pinball. But you know, so playing with that, if you will, in LEO with the 3U, and we'll consider how to get to HEO next based on, you know, whatever opportunities are, or even 1200. Thank you. Good question. Anybody, anything for other engineers? And then I'll cut it over to Mike here. I'm trying to get him not to be able to talk. Ask me questions. Here's Mike. I should introduce you better. Mike Moore is the systems engineer for the Fox Plus program. And he's been doing some amazing work on that for a new guy. But the nice thing is he's picking it up real fast and going with the flow. Disappointments, the hard times, he's just plowing through. So take it away.
Thank you, Jim. So new guy. I've been doing this for about 2 years, and I am a new guy. So it's kind of funny. I love this logo. This is the new Fox Plus logo that Frank Karnaskis helped me with and came up with it, and I love it. You'll notice that we no longer have a apostrophe. No, not a hyphen. God, thank you. I'm fighting a cold, by the way, so everybody's got colds, I know, but I'm on medication. Anyway, yeah, hyphen. And so anyway, I really like it, so. What I want to do today is give you an update on Fox Plus, and I want to talk about the future of Fox Plus, which would be the first time this has been discussed, I believe. So the Fox Plus A update, because now we're going to talk about specific birds. We're going to talk about specific satellites rather than just the whole Fox Plus project. So Fox Plus A, they had this great idea. This was a couple of years ago, just before I came on. And the idea was we were going to use a commercial vendor, which is ISI Space, which I call ISIS all the time, which doesn't sound good. But anyway, ISI Space, a Dutch company, we're going to take their power supply, their solar panels, their antenna system. We're going to take everything that they sell, and we're going to put our LTM in it. And so there's no big deal. This should be a snap. We should be able to do this fairly quickly. And the idea was to get about 5, 6 of these on the shelf as quickly as possible. We'd be ready to fly different payloads, different experiments and everything. And it all sounded well and good. So here on the Fox Plus A, you see the ISIS electrical power system. Those are the components within it, and over there's our LTM. So the big thing here and I'll get more into this, I think, but the ISIS uses, and I understand there was some talk about this yesterday, but the ISIS uses a thing called, their interface is called the CubeSat Kit Bus, the CSKB, and they call it the CSKB Lite. And like I said, we'll get into that a little bit. This does not match up to anything that we use. So we had to come up with a board to interface their power and signals into what our LTM uses, which is why that's highlighted up there. So, besides the connector, the other thing, and I think Andrew talked about this yesterday, but the other thing was the ISIS mounting holes did not line up with our AMSAT mounting holes. And so, you know, when we first looked at that, Andrew and I were like, yeah, no big deal. We just we make all our boards the same as the ISIS boards. We use the same profile, the same measurements. You know, shouldn't be a big deal. Well, it was a big deal because the AMSAT engineering in general decided that we did not want one-off boards. We didn't want boards that were unique only to Fox Plus. Because we do the LTMs for universities. We've got LTMs for other partners, so on and so forth. So we want all the LTMs to be as much alike as possible. Excuse me. So the first thing was that a structural adapter was necessitated, and Andrew did that. We had Dr. Carl Wick did a 3D plastic printed adapter, which Andrew put in. That was the prototype, and found out that was good. And from that, Andrew has done a metal adapter, mechanical adapter, which he's brought. Some of you may have seen that, or maybe handed around yesterday, I'm not sure. So this is the problem we were facing. The holes are off just enough so that we couldn't just easily, make this happen with just an offset. You know, like if they were off by a greater amount, we probably could have done some sort of mechanical offset, which would have worked just fine. You know, spacers. I think we talked about spacers, and so that would have worked. But these are off just enough to really screw us up. That's a technical term. So Andrew came up with the mechanical adapter. This is a picture of it from back when. And then the second thing was as I said, the power and signals did not line up with ours. So we needed a power and signal adapter, which we call the PSA. And that gets the power, and ISIS uses I2C buses. So this gets the power in the I2C buses over to our stacking connectors. I think it was mentioned before, the QXH connectors, I think Kip was alluding to the QSH and the QTH connectors. That's our stacking connectors. That's our bus between the LTM boards. So we have to have the signals there. So the PSA was to get the ISIS signals from their CSKB Lite to our QXH stacking connectors. This is a schematic I did. It's just very simple. It's just, these are just connectors. It's just showing the connectors we use versus the connectors that ISIS uses, with the exception there being the antenna. Right, it's laser. Yeah. So the antenna right there. So you see these H1 and H2. There was a thing yesterday. I wish I had brought this other slide, but I didn't. But the CSQ, sorry, The CSKB light connector that ISIS uses is from the Pumpkin standard. The Pumpkin standard is taken from the CubeSat, the original CubeSat standards, and done by Caltech back when, you know, so on and so forth. So I don't know if Robert's here or not, but anyway, we do not do PC 104. I think this discussion was yesterday. We do an adaptation of the PC 104. I think maybe Eric Skoog, I think, did a lot of that work. We use most of the signals that they do, and they're in the same pins that they use for the most part, but not everything lines up. But we do a lot better job of it than ISIS. ISI Space takes the Pumpkin standard, which, like I said, is based on CubeSat. They take the Pumpkin standard, which is called a CubeSat kit bus, and they eliminated a bunch of signals on there, and they added a bunch of signals, mainly grounds, but they added a bunch of signals on there, and they call it CSKB Lite. This was our first attempt, or my first attempt, at a PSA adapter. At first we thought we were going to need 2 boards because I told you how things don't line up. So the idea here was to have the one board. Let's see if I can do this. But this board would be the CSKB Lite connector. And this is the CSKB Lite connectors here, and this is the ISIS PIU card. So this connector would go in here to light, and that's the full PC 104 number of connectors. That's 104 connectors. But you can see the spaces on the CSKB Lite where they don't use pins. So talking to our mechanical engineer, talking to Andrew, we didn't like pins just hanging out there in the open. You know, that just was not a good way to go. So what we're doing now is we've got connectors that line up with that. But anyway, on this, in this picture here, this is our breakout board that we use. The breakout board has all the signals that we use on our QXH stack, our stacking connectors. So the breakout board's here, and on it is mounted an LTM. The LTM is on here, the 3 cards, the RxTH, the improved command receiver, and the IHU, the LIHU. So again, this was the one connector, and then this was the other, and this was the one that would go to, this was the connector for the CSKB, this was one for the QXH, and then have to have the wires in between. So this was the prototype PSA card that we did, and this is the CSKB connectors up here. So again, you can see that we've got the spaces in between, and this lines up exactly with the ISIS CSKB light. But what we did also, you don't see it on this side, but on the other side is we have the CSKB H1, H2, so you can get the signal names easily. This connector here is for the antenna system. So we put that on this board. This is the QXH stacking connector. So all we needed on this card was the QSH connector. I have to get in. The cabling and wiring within the CubeSat has been identified. We've got the CubeSat physical structure identified. The mechanical adapter we have working, but we've got an issue or two that we're looking into right now. We found out the PSA connecting pins were too long on the CSKB. So we had to get shorter pins. we did that. They were very nice about it. This was Samtech. Samtech was very nice about getting samples to us. We put in the shorter connectors, and Andrew was able to put everything together, and it looked really well, looked really good. Andrew's been working on cabling in Inventor. We were just talking about that a little while ago. And he's done a fantastic job with Inventor. It's a really cool tool, and Andrew's been really good with it. So that's really looking good. This is the assembled Fox Plus A. This is in the building jig that is also made by ISI Space. And this is without the solar panels, obviously. But this is the completed Fox Plus A CubeSat without solar panels. The Fox Plus flight software, Burns was talking about that a little earlier. I say on here 80% complete question mark. I don't know. You know.
It never gets beyond 80% complete.
Well, when I was a project manager, you know, like I would have my Gantt charts, which you know you saw one earlier, and the project plan, and you would be like, you know, well, what's the status, you know, and it's like 60%. So the next week it has to be a little bit more. So 65, you get to 90, and then it's like, you know, you're kind of stuck, you know, it's like, well, yeah, it's still 90, you know. Anyway, so 80%, we're about 80%. So this is a GUI. This is Burns was showing this earlier. You've seen this. This is the telemetry. This is the display of telemetry that he's doing. But this is specifically for the Fox Plus A. So we're working on this right now. We've got some issues on this. So we're looking at a couple of things. Why does it, mainly it's with ISI Space. So we're looking at why does ISI Space do this or do it this way? We would like to see it this, you know, so on. So we're getting there. It's made some excellent progress. We're pretty close. So in summary, for Fox Plus A, we are ready, are very close to ready for the preliminary design review for PDR. And we want to do the engineering model build. We really want to get to that pretty soon. So there's an issue or two. We've got couple of kinks we need to work out, but with a little bit of work, we will be there. And so I'm brave enough to put up some dates, you know, and, you know, I asked Jerry about when I did this. I said, you know, do we really want to do this? Thing is, people haven't seen dates for Fox Plus too much. So, so I'm putting these dates out there, and these are, I say, tentative. They're kind of, they're tentative. Yeah. So I'm hoping to do PDR in the November-December timeframe.
I said they do look pretty good, but there's always what else.
Yes, right. Okay, yeah, he's saying that they look pretty good, but we've got these what ifs and these little issues I was talking about, little things to work out. If assuming we do the PDR November, December, we hope to get into the engineering model system testing in the January timeframe, and the flight model build and test March, June. Final testing, July through September, and launch something in December. Ready for delivery, yeah.
Right, because it's hard to say we're going to launch on certain dates.
Right.
Most tentative thing I'd say.
Mike, can you repeat what Jerry's saying?
I say, yes, I'm sorry, but as far as launch, I mean, I just talk about launch of Foxes, and then pretty soon I couldn't talk about the launch of Foxes. It's because CSLI, or even a commercial launch, which is down the road quite a bit, we don't know when they're going to launch it. You know, you give it to them and they sit on it for 3 months or something. So delivery date is what I call it now, and that would be what I was coaching him to say. It's ready for delivery, integration.
Yes. What he said. So that's Fox Plus A. So now I'd like to get in a little bit to the future of Fox Plus. And again, this, I don't know that this has been presented before, so drum roll. Okay, Fox Plus B will be the second and likely the last AMSAT satellite built on the ISI space platform. The reason being, we don't like it. Yeah, it's a good company. They do great. They do some great things. But we would like to do our own thing, and they, right, you can't buy it the way we want to do it, in a nutshell. So, but we've got two sets of everything. We've got two sets of the solar panels. We've got two sets of antennas. Actually, I've got a third. But anyway, we've got two sets of everything. So we want to go ahead and use them. It's very expensive stuff, as I'm sure you know. So, so Fox Plus B will again use the ISIS system, the ISI space components, I should say. Here is a conceptual block diagram of Fox Plus B. So Fox Plus B is the PACSAT satellite. So we are wanting to put PACSAT. I don't know if PACSAT's done a presentation here, but it's digital. It's a digital satellite. There's a lot of interest. When I was at Hamvention, a lot of people, they come up to the booth and they're asking about geo, but the second thing is digital, and there's a whole lot of interest in digital. So we're working with the PACSAT guys right now. They have, they've actually done a prototype. They've got a board, they've got things working, and things are looking really good for them. The issue we have is fitting them into the 1U satellite that's Fox Plus. Using the ISI space components, we had to do the mechanical adapter, and we had to add a board that's the PSA card. And so you've got that in the LTM cards. We don't have room for anything else. We've got no room for a payload. We've got no room for anything else. So we can remove the transponder, the transponder card, the RxTX, in the LTM, and replace it with the PACSAT card. And on here I show the ICR and the LIHU, so I will have to see if we can fit all that in. Excuse me. So if we can't, if it becomes too difficult to fly PACSAT on Fox Plus B, then we will push PACSAT and the digital satellite off for a later bird. But we would really love to get it on Fox Plus B. This is the PACSAT block diagram. This is this is their kind of generic. This is what they've got right now. This is not exactly what it would be on Fox Plus B, but it's close enough. You get the idea. So they have, you can see they've got 4 receivers, 1 transmitter. They've got their own transmission stuff there. The power supply would not be there. There's power components, but it's not really a power supply. Anyway, you get the idea from that. So, when might this happen? This is very tentative. We want to start Fox Plus B as soon as we've got Fox Plus A on the path to finishing up. So when we've got the flight model for Fox Plus A going, and we think we've got it pretty well in hand, we will start the engineering on Fox Plus B. Again, we're working with the PACSAT guys, and the thing would be putting it into our satellite. And again, if we can't get PACSAT in there, it'll be on a different bird, and we would then fly the linear transponder once again, which is what Fox Plus A is. So this would be March of 2026, cross fingers, with the PDR somewhere around June of 26. And these dates are fairly close together because we've already done Fox Plus A. So the big thing is once we've got this figured out how to get this into the Fox Plus, then it should go fairly rapidly. So again, and it shouldn't be launch on here. This should be ready for delivery around March of 2027. So a little bit over a year from Fox Plus A. No, I'm sorry. It's only 4 months or so after Fox Plus A. Yeah, thank you, somebody. Excuse me. Okay, so then we've got the 2 ISI space birds, and those have we've gotten them done for Fox Plus. Fox Plus C, or whatever we call it at that point, I don't know if we keep with the alphabet. I don't know if we go to Fox Plus 3 or... Okay, then we'll keep the Fox Plus C. And beyond, we would like to, again, engineer our own Fox Plus. And the thing is, with the engineering team has talked about with the demise of the CSLI program at NASA, which is a shame, but we have to start planning on paying for launches for golf, for all of our satellites. And it's very expensive, although I understand the prices are coming down a little bit, the costs are coming down a little bit. But we were told a little while back that a good model, a good ballpark estimate, rule of thumb, whatever you want to call it, be about $100K per U, $100K per 1U. So a 3U CubeSat would be about $300,000 per launch. So Fox Plus being 1U, or we'll get into some other stuff, but is a less expensive platform. So, of course, Golf T is flying experiments, and Golf T will be a step off onto some really, really great things. But there's other experiments coming up that we're going to want to test, and we've got people wanting to do things. So the Fox Plus program will become kind of our go-to program, with the going back to the concept of having these things on the shelf and being able to fly things when people need them. We would do our own in-house frame. EPS, EPS we would probably use like a takeoff on Kit's EPS from golf, and solar panels, you know, roll our own. So this be really fun, and we're talking about. Oops, let me go back. I thought I had something in between. Anyway, I'll just talk to it. The thought is that 1U is kind of disappearing a bit, and it's getting more expensive. People are, excuse me, the dispensers that these CubeSats go into are typically like 3U. And so we're talking about, let me get some water, excuse me. we're talking about going to a little bit larger units, a little bit larger birds. So maybe we would go to 1.5 U, maybe 2U. But if you go to 2U, you almost need a 1U. Anyway, there's even talk of going to 3U. But then you're kind of into golf territory. But by that time, maybe golf has moved on to 6U or something. You know, they may be off on. Okay, yeah. Jerry says he wouldn't let golf being 3U stop Fox Plus from being 3U. So anyway, we're talking about making it larger. One of the big reasons, I thought I had a slide in here about 2U, but I don't. But one of the things is just so much more power. You know, the 1U you can only put easily. Only put your solar cells on the panels, on the exterior panels, and so you've only got, you know, so much power. I think I don't want to give you a number because if I get it wrong, but you only get so much power. When you go to a 2U even, you can you've got all kinds of, you know, it's much more than twice the power, and you have you can do fold out panels. You can do, I've seen them where they have drop down panels. You can do just all kinds of good stuff. So it gives you so much more power for the payloads. So the idea would be for the Fox Plus to be doing payloads and experiments, which that might require a different bus. Right now we've got the QXH bus, which we've talked about a number of times. It's the 60-pin bus that goes between the boards on the LTM. Excuse me. But now we need to turn experiments off and on. And depending on how many boards we've got in this, we need to be able to turn these experiments on and off. And so that may require a whole different connector. Instead of the QXH connectors that we now use, we may look at different bus connectors, and Eric Skoog has said that there are some very good bus-oriented connectors available. That, you know, things. I mean, the QXH technology is a few years old now. It goes back a ways. So there's things we can do. Anyway, it's very exciting. It'd be very, very cool. To be doing this, and so I put some dates down on this. But now this is just a WAG, and that's a technical term too. And so we would like to start on this in September of 26. And then you notice these dates are pretty spread out, and that's because we've got to design this. We've got to design the whole thing here. You know, we've got a whole new set of designs we have to work on. So looking at this, we would like to be able to do something by maybe the end of 27, ready, you know, ready for delivery by the end of 27, something like that. And I think, oh, here we go. Here's my other slide. Yeah, the 2U. R3U, and then I already talked about all this, I believe. And yeah, we've got, the thing I did not mention was not only do we have universities that are looking to do experiments with us, and STEM, which Jerry talked about, but we've got scientists on staff. We've got university scientists on staff who they're like, well, I've got some ideas, you know, and we would like to be able to do some things with them. Are there any questions? Yes. Okay. Okay.
Any thoughts at this point for Fox Plus C as to what kind of RF equipment you're going to put on it?
No, we not besides the experience, but yeah. Multi-channel FM.
All right.
Yeah, thank you.
So I understand the interest in not having multiple versions of the various boards for different mounting holes. But I'm just wondering why we couldn't have our boards avoid any components or wiring in the corners at all, and then we can just have a single board, and then we just drill it for whatever the hole spacing is at the time we need it. You know what I mean?
No, not
So instead of having a board with hole spacing for golf, for the golf standard, the Fox standard, and the ISI space standard, which is different, right?
Yes.
We just keep our components out of the corners,
Right.
and then we can drill holes in the corners wherever the heck we want them.
We actually
And then
do.
we only need one design, and then at the time of use, we can drill the holes.
Yeah,
know what I mean?
yeah, but it just doesn't, the geometry of it just doesn't work out. We can't, like with the ISI space, we can't just, it's not just the mounting holes. In my presentation, I said the mounting holes. Sure. Because it's not just the mounting holes. The boards are different size. Ours are 92 by 92, and the ISI space is 92 by 97.
In the case of Fox Plus A and B, it's because our boards already exist for it. And so that they've got our whole pattern, if you will.
Already there.
Right, and in the future Fox Plus C, et cetera, having our own bus design has proven to be extremely versatile for over 10 years, way over 10 years, for what we like to do. So honestly, I don't see that there's going to be a commercial thing that we're going to want to stick it in that's going to satisfy us right now.
Right, that's why I was suggesting we just keep all the components out of the corners in general, and then whatever happens in the future, we have room to drill. But anyway,
And
we
that's
can
a
talk.
possibility, but boils down to we like to cram so much stuff on it, so it kind of depends on that too. Right?
But we do have on the corners, we do have a no component zone. And that exists right now. Yes, sir.
Since you're talking about future missions, I wonder if there's been any thought of loading up, say, a 3U worth of space with multiple satellites, 3 1Us, a 2U, and a 1U, and then those would slowly disperse.
Yeah, you mean in the dispenser? You mean
in one dispenser.
Yeah, that's what we're trying to do. We do try to do that, but that's the problem is you've got to find somebody with a.
My point is, all of these would be AMSAT satellites, like 3 1U AMSATs.
Right.
And then those would slowly disperse in that orbit.
Right.
There might be some interesting things you can do there.
Yeah. Yeah. Okay, more on that in the general meeting, says our new president. Yeah. We've. I think they're going to talk about this a little bit more later, but I've heard talk about doing 1.5U and doing 2 of them at 2 at a time, kind of thing.
What I was talking about is purchasing 3U worth of space in a dispenser.
Right.
And then filling that with
multiple
AMSATs.
Right. I think we're going to get away from 1U though.
Oh, and it takes a long time to make even a 1U, so it would take back to Drew.
Yeah, Drew's going to talk about it.
Yeah, that means he knows something I don't. Go for it.
So, kind of along similar lines, thinking about the marginal difference between a 1U and a 3U in terms of launch cost, I think that's probably a good reason to also maybe avoid the 1.5 and 2 unless you're able to package multiple of your own satellites together. And one thing is 1.5 is really hard to match up with because it's very rare to find another provider that's doing 1.5. But where it does kind of work out is if you have 2 1.5Us that you want to fly together, then it can make sense. But it's going to be very rare to find kind of a matching 1.5 somewhere else.
Yes, yeah, no, understand. It's sounding like we should go to 3U, but that's just me.
We'll work it out.
But we'll work it out. But the point is, Fox Plus has a very good future aside from golf. It's golf is is a complex bird. It's it's got so much on it. It's very cool, and it's going to continue. And they're going to they're going to be doing good. The Fox Plus will continue to be kind of not nearly as sophisticated, not nearly as complex, but would fly, like I said, would fly payloads. It'd be like the mule. It'd be the guy to take stuff up to test it out. That's kind of the vision, if you will. Any other questions? Then I'll turn it back to Jerry. Thank you very much.
And thank you for all the questions for him. As far as the nomenclature, or how many satellites we're going to make or put into something else, there's also, if you talk about immediately, we can give an answer to it. But for future, really a lot of that depends on what the board of directors and president and such has to say about it. So that's why it would be a good idea to defer to him on that. So I would like to have in maybe 10 minutes, 15, talk about the ASCENT and future programs that we're working on. ASCENT is the acronym for Advanced Satellite Communications and Exploration of New Technology, aka Skunkworks is what Tom Clark originally called it when he thought of the idea. We've got 3 programs active in ASCENT right now: SDRB, aka SDR Gen 2, and Microwave Ground Station, which I mentioned, working on initially to be able to work with Golf T to receive, it works for VHF, UHF, as well as the 10 gigahertz downlink, and then future of 5 gigahertz up. And also in the future, that would be to expand out for higher satellites. And propulsion team, again, you've heard from them and even seen from them, so that's cool, but they're doing some cool stuff. I'm into railroad steam engines, right? And so when they said steam, I was like, oh yeah, let's go for that. We have some products, if you will, and partnerships. These are the things we're wanting to make to go on the shelf, like LTM, PACSAT. So we have, and the reason the question mark's there is simply because I didn't know when I wrote the slide, but an LTM that has been promised to University of North Dakota, and they're going to fly it on their joint Cape 4 mission with, is your university, is it of Louisiana? Yeah. Okay, University of Louisiana at Lafayette, Nick Pugh, and PACSAT, we expect to have them on the shelf for Fox Plus B and whatever else. So in total, in maybe a year even, into 2026, hopefully, we'll have 5 LTM, 5 PACSAT, or close to that, and 5 SDRB available to give away, because there's a lot of launch opportunities that we don't have to build a satellite for as well. As a matter of fact, opportunities that we couldn't meet because we didn't have something to just hand over and stick on a whatever launch vehicle, et cetera. So that fulfills part of our mission right there, is to be able to carry on stuff and while we go tinker with the satellites. Sorry. Something in the air here. SDRB, as I mentioned, Ray Roberge, he actually, even years ago, he was talking about this at Symposium, what he was going to do, what he was capable of doing with the EDIS E310 that's flying on Golf T. And you see a picture of it there. And cover off, see, again, we couldn't modify, we weren't allowed to modify any of the PCBs or layouts in order to shorten it. The SDRB is going to take that and condense it down into a 492 by 92 format, and it could fly on Fox Plus, whatever, Fox Plus something, and hopefully intended the first shot at it will really be helpful on Golf 1, because then, see, Golf T is it's a temporary bus as well, avionics bus, because we got that transverse stack, because we have the Edis radio in there. So to have everything put into a row again, that make it a lot easier to put together, a lot easier to lay out as far as what you're going to put in there. And so I'm looking forward to that we will plan on having that to fly on Golf 1. And Golf 1, of course, will exercise with the 10 gigahertz. It'll be LEO, but still 10 gigahertz, 5 gigahertz up, 2.5 gigahertz up, 2.5. So everybody around the world basically could use the microwave portions of it. That does block that. Status for the SDRB. Yeah, Ray, and this is an incorrect statement I put here, and I was corrected in the board of directors meeting the other day, but Ray I thought he was looking for some software, but he was actually offered some software for what he was looking at in the FPGA. Again, intentions to fly on Golf 1. The microwave ground station, there's not a new update to it. Jonathan Brandenburg's working on it, and he initially proposed that he was going to start with a part by part to make it as cheap as possible, and also that would give it an expandability, so you could go, well, I'm going to build the 10 gigahertz part, and then when we can do 5 up, I'll build the 5 gigahertz part. One of the things he's hung up was on the tracking, but he found that trying to get source commercial parts to be able to put something together was very difficult, to be able to come up with good combinations of things, for one thing. So he kind of switched directions on that a bit, revised approach, and he's looking at SDRs like Pluto, Lima SDR, and transverters instead of each single band. Could be opportunity to mix bands. He's getting help from the microwave update that he attended, but also he's a member and located close with the North Texas Microwave Society. So the fact that we get them involved, which wasn't too hard really, with people like that being advisory, NTMS, that helps a lot too, and because they're the people who are going to want to go, yeah, we're going to try that out, right, initially, and then that helps to grow the equipment that's available for the rest of us who, at whatever level, want to join in. And I said the antenna tracking is a challenge. It is, because for the 10 gigahertz at LEO, with the pointing accuracy that he's needing for the high-speed data downlink, there aren't any rotators that most of us own that are capable of doing it and moving as fast as they need to. So it's a trick, and he's also working with Ray on that. Ray Robert has devised some ideas for using a beacon signal as a Doppler tracker to automatically adjust Doppler and such. I'm sorry. So the propulsion, I don't know if I can say much more about it than what's there, huh? Various backgrounds. These gentlemen are located in a good spot because they're close to that company that they were demonstrating yesterday. They are all, I think all, in the same area themselves. Is that true? Well, except for one guy over there. but no, I mean, at least they've got access to and abilities to get the stuff. Originally, they mentioned, I think, that Jonathan had procured an electric propulsion type of thing that they started working with, but if that doesn't work, and yeah, always that's a concern with radios, even if we fly LTM, if we're flying it on somebody's satellite that's got electric propulsion, we theorized at least at one time that the HuskySat, which was the University of Washington, the first LTM to fly, that had trouble may have been affected by high EMI levels from their electric propulsion that they had designed and were testing out. So, don't know that. The trick when we're flying a radio on somebody else's satellite, essentially, we want to give it to them. They can get licensed and they can learn about ham radio and license it and operate it, and we get a radio without having to build a satellite. However, that means that we don't know what's going on a lot of the time with what's going on there, especially if they're doing experiments that they want to kind of keep to themselves, which they don't do over ham radio. We won't let them do that. But so it's one of the side effects of that. MESAT, if I can say it, just kind of disappeared, and we're not sure why, right? So there's that factor is what I'm saying. So if we give somebody an LTM, PACSAT, whatever, and it doesn't work right or stops working, it may not be our fault at all. Of course, he'll call us, but what the heck? What did I miss there? Yeah, let's see. So the propulsion overview, we have, we have the orbital debris regulations that are in effect now. They don't say that if you go above about 500 kilometers, or 600, you should be able to maneuver to be out of the way of, collision avoidance. They don't say that yet, but I don't expect that by the time we can get there, I expect that's going to change. And talking with Space Track, 18th and such, that's a strong feel. Also NASA. So, like I said earlier, if we fly something right now to HEO or whatever, it's not going to be our rockets and stuff, but learning how to do that can give us a lot more freedom in the LEO, upper LEO, if you will, that we can't get to right now. And it can make a pretty good difference in footprint even, getting up another 100 kilometers or something. I'm going to skip this, says the steam propulsion team will be presenting here, so that means you guys got to do another show. And I know it does block that. Oh, yeah. Well, I covered this. I'm trying to leave us a little break before Drew talks. And again, the partnerships. We've got LTM with North Dakota. You did have a CSLI, if I can say this, right? And it was canceled as well, correct? So we're in the same boat in that sense, but just like us, you're looking for a launch, so we're still going to give you an LTM pretty soon. What the holdup is on that, in a sense, is that we want to have that final version of LTM, and it is in work. It's not put together to where we can just hand one to somebody yet, but they'll be the first, and so they're going to get the latest version, the last version that we expect to be able to go out. What version would it be, Burns, there? 3. That's a good number. I like that. Version 3, and then it kind of gives us that ability to help others, provide radios to others, and concentrate more on this. Because again, our resources are kind of like we've taken people away from golf to work on Fox. We're going to take some more away from golf and possibly Fox to work on LTM to get it done, unless we have more volunteers. So, I mentioned volunteering for, talking to any of the engineers here about what you saw, but you can certainly inquire about anything that your skills are. Self-starter, you're experienced in whatever field, and send us an email. Volunteer at AMSAT.org, sorry. And the PACSAT going on Fox Plus B. That has been underway for a little while. They do have, recently I approved the purchase of a bunch of PCB for assembly and then testing. The volunteer said he'd be testing them over his week after Christmas break. And let's see. Yeah, that's what we're expecting on the shelf. I'm afraid that kind of trying to combine some of the board of directors slides in here. I kind of duplicated some stuff, but that is the last slide. But I ain't going. No, if there's any other questions, this would be a great time to ask. We got a few minutes. I think there's supposed to be a break in about a few minutes. Did you have a question? Oh.
Yeah, Jerry, we have a question from the YouTube stream from Perry Klein, W3PK.
Oh, hi.
He had asked if the satellites are designed to, if any Golf or Fox Plus are going to be designed to disconnect the battery if the battery fails. I know that's been a recurring question throughout the development of Fox. Just wanted to know if that was being designed into the next satellites.
Yeah, ever since I was a baby, as far as being in AMSAT engineering. No, we haven't figured it out yet. Just kidding. Kip explained pretty well, and if there's anything you missed, you can ask the question, but yeah, we're going to expect that out of him for Golf 1. Go ahead. You can come up. Oh.
Yeah, we have to be completely disabled from the batteries when we're in the dispenser. So I'm using the exact same cutoff for when it for when the batteries die. We can isolate them off using the same switches to let us run just when we've got light once the batteries are have died.
Is that commanded or automatic or both?
Commanded
So
at the moment.
We're halfway there.
Yeah.
Okay. Yeah, well, we'll be able to, see the NICAD, the Fox 1 did not have near the telemetry, the capability, the control that we're going to have over these batteries. So it would be a lot easier to sense there's a problem coming and to go ahead and take care of it before it happens. Wanted to add one thing. I was informed that the possibility of choosing LiPo versus LiPo batteries could be the density, the charge density, and because we're liking to pack as much as we can in there. There is a suggested limit to the chemical stored energy when you're going to be on a launch, and I think it's to be less than 90 watt hours. In which case, if I understand correctly, we would, have our batteries at a state of charge below that. But I think the 8 cells is capable of giving us 100 at full charge, 100 and something watts. A funny thing is on that S-28B launch we had, they asked for that number in kilowatt hours. So 0.140, I figured they're never even going to see that on here. That's pretty cool. But yeah, we have to be mindful. It varies by launch provider. So we're always good citizens for whoever's launching. And if I find out more, I will tell you for sure. But that's what I know right now more.
All right, Jerry, thank you very much.
Thank you.
Mike, and the entire engineering team. Appreciate the information.
Thank you.
Okay, at this time, we're going to take a 15-minute break, and then please be seated for our annual AMSAT member meeting.
Welcome to the welcome to the general meeting for AMSAT, members meeting. We're gonna start out with, Bruce Page is gonna come up and present the awards for field day, and I think he's got a couple other things.
Thank you, Drew. Let's see, I've got a 10-page report here. Let me get it out.
The more time you fill, the less I have.
Okay, we can make it last. Maybe. Oh, there it is. All right. Let me put this phone in my pocket. All right, this year we had 17 stations participating. Not very many. We've had more in previous years. 17 satellites were in operation. I consider a satellite based on their mode of operation. So if they have a VU operating and they also have digital operating, that would be 2 modes. If they have sideband, you've got your sideband, you've got your CW, so that would be two satellites, basically. We had a total of 463 QSOs that were made, and 503 points total earned by all these stations that were operating. So our third place winner for a club station on emergency power was the Huntsville Amateur Radio Club, K4BFT. Big Fat Turkey, as they like to be known. And anybody hear from there? Oh, we get something to mail. All right. Then for second place, we've got the Huntsville, wait a minute. Yeah, second place is the Holland Amateur Radio Club, K8DAA. Anyone hear from there? No? Yeah. And first place, Lafayette DX Association, W9LDX. They had a total of 118 points. So they usually stay up there in first or second, third place. They jockey around every couple years. And then we have the first place for home station on emergency power. We just give one first place out for that. We don't do second and third. And this goes to George Jones, W2GDJ. Anybody around him? Good, 4 certificates to mail. Now I got something special. Oh, for the first place home on commercial power, that was me.
I don't care about the certificate. In fact, I had the same number of points as George did there. Now, the VUCC, reverse VUCC, VUC stroke R, that's been around now for a few years, and AMSAT is now managing it. And the person with the most is N9DM, Jim Carey. He's got like 494 grids because he was mainly operating from a ship. So he had a whole lot of maritime grids. But I got a little sticker down here all the way at the bottom of this envelope. I may just give this guy the whole envelope. Randy, and he used to be N7SFI, I still remember that. Now he is W7IP. He's number 2 on the reverse VUCC, and here's his sticker for 475 grids. He'll hit 500. What was your? How far did you travel this last month? What did you do on that rove?
Around Maine?
Yeah. How many miles?
I'm going to say 7,000.
There you go, 7,000 miles to earn that certificate or that endorsement. Thank you. Back to you.
Randy's been doing that a long time. I can remember 20 years ago working him on a HT and a whip. So I want to introduce our current board of directors and senior officers. Obviously, you know who I am. Thank you very much for the opportunity to serve you as president this year. I want to introduce our executive vice president, Paul Stetzer, N8HM. Paul's in the back of the room helping running things. I'm going to be leaning on him quite a bit this coming year. And our vice president of operations, brand new, Mark Hammond, N8MH. Mark's been my right-hand man for quite a while, as I was the former VP of operations, and I'm sure that he's going to fit right into the job, and it'll just be like old times. Vice President of Engineering, Jerry Buxton, N0JY. Our treasurer, Steve Belter, N9 India Papa. Unfortunately, Steve couldn't be here this weekend. Our secretary, Doug Tabor, N6UA. Our Vice President of Educational Relations, Alan Johnston, KU2Y. And back running the board, Frank Karnauskas, our Vice President of Development, N1UW. We're currently have one vacancy in our officers list. We're looking for a VP of User Services. If you have a penchant for being abused, come on up and talk to me afterwards, and maybe we can work something out. So our board of directors for this year, Barry Baines, WD4 ASW. Jerry Buxton, N0JY. Myself, Mark Hammond, N8MH. Frank Karnauskas, N1UW, back in the back. Bruce Page, KK5DO. Paul Stetzer, N8HM. And then our first alternate is Doug Tabor, N6UA. You may have noticed there's a little bit of overlap there. And you can probably figure out who does like to be abused. Folks, don't be afraid to run for the board of directors. Don't be afraid to step up for a leadership position. Ideally, those two Venn diagrams shouldn't overlap much at all between the officers and the directors. But it is what it is when there's a limited amount of people that are willing to step up and help out. That's what you get. So, all right. Normally, the president at the general meeting would be talking about what AMSAT has done over the past year. I kind of feel like we've done that all weekend, haven't we? So I'm going to be talking about what I would like to do, what I would like to do together with the other officers and the board moving forward this year. And I presented this in the board meeting, so if you sat through that, I'm sorry, you're going to have to see it again. I did make the type font a little bit bigger, so hopefully everybody can see it. I've got a header that goes through all these. Problems equals opportunities. If you don't turn problems into opportunities, they remain problems. So we're going to go through a couple of different areas where AMSATs have some challenges right now. And I'm going to talk about what I think we can do together to fix some of those, and maybe go into explaining some of what's happening that you don't see in the day-to-day. Membership organizations are in decline everywhere. If you follow any organization, the ARRL, you know, anything that's a membership, national membership organization, most of them are struggling to keep their membership numbers up. And a lot of this is due to differences between the generations. And, you know, I'm a solid Gen X. I'm probably a little younger than most of you guys. So I kind of have a foot in both of those realms. People used to join organizations to come to conferences like this and collaborate and have a good time with their fellow members and people of like minds. A lot of that happens online these days. If you look around this room, we've got about 50 people in here. The first AMSAT Symposium I went to, I don't remember the exact year, I think it was 2002, something like that. It was in Fort Worth. Keith would pop me if I said Dallas. 2003. And there were probably close to 150 people there. We had, was it Lockheed's facility? And I remember at the banquet there were a dozen tables with a dozen people apiece at them, or maybe bigger. So we've really drifted downward in the 20 years that I've been coming around to these things. Do we really need to be, this is a big jump, do we really need to be dues driven? Over the past 5, 6, 7 years, Joe and Robert and the rest of the leadership team, we've made a push to save money and bring the organization forward. New things like membership database, the office closed, Martha retiring, you know, those two things are side by side. The journal gone digital. We don't pay to kill trees and ship them around the country anymore. That was a significant expense. All of those were significant expenses. So we've saved a lot of money in the day-to-day running of the organization. So can we reduce the membership cost in response to that and perhaps bring our numbers up and make it easier for people to join AMSAT and gather the benefits of being an AMSAT member and support AMSAT and its mission? My idea, and we need to look at the numbers on this, is AMSAT has been the beneficiary of several large estates over the past 3 or 4 years. We have a pretty good financial statement right now. We've got between 1.9 and $2 million in the bank. Perhaps we take half of that and set it aside as an endowment, and the profits, yearly profits off of that, go to running the organization and as an emergency fund. And that would allow us to lower the cost of the organization. My predecessors have often, and Barry in particular, have often pointed out that the organization runs off the dues, but projects are funded off of donations. And I think we can take that dues part and bring it way down. I think it'll also, and I'm not just talking about ARDC here, I think it'll also look better when we look for grants and outside support, that we don't have $2 million sitting in the bank. We can separate those out. This is our operating fund and this is our endowment and long-term fund. So I'm not a financial expert, but this is an idea, and I think I got a pretty good response from the board on it. So we're going to check it out and talk to some experts in the area and see how we can make that work. So I'm hoping we can lower membership costs by at least 50%. $44 is still a good chunk of change. 25 is about like a Big Mac meal, so maybe we can lower the cost of membership and make it easier for people to decide to make that commitment to the organization. Pushing a little further, because my intent here is to push things a little bit further than they have been. My intent is to rattle some cages if possible. Perhaps we go to a 2-tiered membership, which would require some work with the Articles of Incorporation. But maybe we have one free but non-voting member, and then a donor class or a membership class, where if you donate so much per year, you get a vote. So some way to bring people in under the umbrella and grow our ranks. Something we can do immediately is we need to create a membership committee or a membership manager, hopefully with some additional volunteers under the manager. We can do an immediate membership drive with digital getting started. Costs us nothing to distribute it. It's a nice perk. We've done that around some past launches and seen very good response out of that. Unfortunately, we don't have a launch sitting on the pad, but we can do what we can and try to bring some more people in. Long term, some of the ideas I've had about it is that we be more proactive when we hear somebody new on the satellites, reach out to them, invite them to join the organization, give them an idea what AMSAT does for the community. Youth. This is a big one for me. I don't know if you guys know. I have 2 kids. I have a 13-year-old son, Karsten, KQ4 SJM, and a 15-year-old son, Willem, KO4UWY, or UYE. I've tried to get him to change that one. Both of them somewhat active on satellites. So it's near and dear to my heart. I want to see kids involved in the organization. Frank's doing a wonderful job at that, and he's about to let loose some really good stuff. I think there's more we can do. We did a couple of years back lower kids membership, students membership, sorry. Primary through a master's degree, we lowered it to $22 a year instead of $44. We have approximately 45 youth members. That's about $1,000 a year. $1,000 a year is not much. That was a couple trays of the stuff we had last night at the banquet, or the thruster firing. So I proposed to the board that we make primary through master's degree students up to the age of 25, free membership. What do we have to lose? It doesn't cost us anything extra to email them a copy of the journal. But the more kids we can get into this organization, the more students we can get into this organization, the more college students working on CubeSats that we might get into this organization, the better we are. Because as a couple of people have noted, look around. There's nothing but gray hair around here. I mean, really. So I'm proud to say that the board did approve that at the board meeting yesterday, or day before yesterday. So a couple other things we can do right away. We can reinstate the college activity night. We used to have a night once a month where all the college stations and college students would get on. We can expand that to youth, and they would get on and work each other, and it was really pretty cool. And when AO51 started deteriorating, that kind of slipped, and that is 100% my fault, and we're going to fix it. And I would encourage you, once we get that rolling, to get on the air that evening and work some of these college kids and some of the youth that'll be on. I want to establish an AMSAT YouthNet. We can do it via Echolink. If good satellite passes like RS-44 line up, we might even try to do it online or on the air. I want to see a youth column established in the journal, and I'm volunteering my son to start out. How's that? I hope he's not watching at home right now. Yeah, he knows about it. There's a lot of things that we do that are simple to do. I mean, altogether, going out and copying a slow scan image from a satellite or from the ISS is pretty damn exciting. I mean, I even get wound up about it, and the kids love it, and we've done that. So, you know, a simple article about this is how we do it. You know, you take your HT, you take your phone with your program on it, you can hold them together, you can record, you know, anything like that. Anything that the kids might be a little bit interested in. Simple antenna projects, radio hacks. My son loves to take a brand new radio and get into the firmware and start poking and peeking and doing all sorts of stuff to it, stuff that I don't even understand. RTL dongles are cheap, easily accessible. We can talk about WeatherSats, LoRa, Meshtastic. These are all things that have some interest there that we could provide and cater to the younger members in the journal. We'll have to tell them how to read a PDF because they're probably not used to doing that, but more activities targeted at CubeSat builders, students, some ideas. I also wear another hat. I sit on the IARU Satellite Coordination Committee. We see 10 to 15 student satellite applications a month looking for coordination. And of course, we also peruse these to make sure that they're aligned with the amateur radio service. There's a lot, they don't know what they don't know. And there's a lot of times that in trying to provide an amateur service, it doesn't come across very well. We get digipeters that nobody can really use or want to use, or you know, they think that sending a beacon is a service to the community, which it is, but it's kind of at the bottom of the bucket. So, you know, maybe a grant for establishing a two-way mission. We can continue to push the LTM as a possible solution, and once we get some of those on the shelf, that's going to be even easier. Sponsored symposium attendance, either funded by us or by somebody else. You know, symposium is not a fixed cost per person, or a fixed cost per event, but we can afford to get some young people in here and learning from us and us learning from them. We need to do more CDW presentations, demos, things like that to let people know what amateur radio really is, and especially amateur radio in space. CSLI. Man, what a kick in the gut to lose a launch. We've had 5 launches recently, or 5 CSLI launches that we have benefited from. AO85, AO91, AO109, HuskySat, MESAT, both of those carried the LTM on board. We may get them back. CSLI is not dead, not quite yet. It may be replaced by some other program. There are other programs out there that are similar but less well known. We need to investigate those. We've paid for launches in the past. AO92 and AO95 were both launched by Spaceflight Services, just because we got kind of tired of sitting around waiting for AO85 to launch in 91, so we went out and bought some launches. LEO launch costs are not insurmountable. They have come down since we bought those 2 from Spaceflight Services. Golf T has had a significant investment. We should finish the satellite and pursue a commercial launch if CSLI does not come back in a reasonable time frame. And I think we can look at several different places to help fund that. If we have to fund it out of our own pocket, I refer you back to the $2 million in the bank account. That's what that money is for. LEO, low Earth orbit's becoming increasingly difficult to operate in. The orbital debris rules since I've been around have went from nothing to 25 years post-mission to 5 years post-mission. So if you look at the satellites that were launched in that time frame, some of them were at 1,500 kilometers. And then with the 25, we came down to underneath 800. And these are rough numbers. Please don't, I rounded to one significant digit. And then 5-year, we're looking at 550 kilometers. That does several things. That reduces our footprint, and reduces our access time, and it reduces the lifetime of the satellite, obviously. That's the big one. There's a lot of re-entry devices. People ask me about them a lot. A lot of them are unproven. I think they're coming around, so that might be helpful in the future. But the big problem is the bus, the launches that we can afford. They really don't stop too many other places than 550. The bulk of the small satellite launches now are on Falcon 9 transporter and bandwagon launches, with a few on Neutron and a few scattered here and there otherwise. But Mr. Musk has got the market pretty well cornered. If you go out, if you did have a deorbit device and you went out and tried to find a launch, a ride share launch to 1,500 kilometers, they're just not there. On a related note, in 2023, the FCC fined Dish Network $150,000 when one of their satellites reached end of life and they moved it out of the geo belt. They did not get it all the way to the approved disposal orbit. Dish Network collects enough money from enough people that probably $150,000 is kind of a drop in the bucket. The last 4 satellites that we've had have been licensed to me as VP of Operations. FCC does not license amateur satellites to individuals. That's scary. I just say it, it's scary, if our satellites are not maneuverable, if we have a conjunction with somebody else and they have a nastier lawyer than we can find, we could be on the hook. So, LEO's tough. We're likely, as Jerry said, we're likely to see propulsion mandated for avoidance maneuvers and debris mitigation soon. And we have not yet done that on a CubeSat or a microsat for AMSAT purposes. Here's a big one, and we've seen this coming for a while. We're all volunteers, and when we decide to build a satellite and put it together, it's not something that we can just drop everyday life and go do for 3 months until it's done. But we have development times that stretch as long or longer than the time on orbit. And that's not sustainable if you're doing one-shot projects. If you're building an entirely new satellite and it takes you 5, 6, 7 years to put it together and it lasts 2 or 3 years, that is not a smart investment on our part. It's not a smart investment of our engineers' time or our precious money that we have in that bank account. Fox Series really avoided this because we built 5 of them. We went from a single CubeSat, AO85 was planned, or Fox 1A was planned as Fox 1, and it became 1A and 1B and 1C and 1D and 1E. We got a return on our investment on that. So we have to be careful of this moving forward. And it also led to at least 2 adjacent projects with the LTM, which came out of Fox 1E. So to maximize that return, we need to plan our LEO projects to be a series of satellites from start to finish. How thrilling would transporter goes, SpaceX Falcon 9 transporter launch, which is the dominant launch, goes once a quarter. They're on, 15 or 16 now so far, and they're about once a quarter now. Wouldn't it be awesome if we had something on every launch? Once you build it and get the design down, then you can make little tweaks along the way, which is what we did with Fox, but I'm just reinforcing that this is the way we need to operate. Iterative improvements. Again, referring to Mr. Musk, Starlink, Starship, how many Starships has he toasted? And every time he tweaks something a little bit better, they tweak something a little bit better. Another way to solve this is that we start looking for payload opportunities in lieu of entire satellites. Regulatory and operational burden is lessened. If we have a partner that wants to fly a mission that may involve some STEM and STEAM, may involve just a repeater or a transponder or a digipeater or whatever, and they're flying a 6U satellite and they got half a U available, and they're willing to carry us, maybe for a small fee, maybe for something in return, some quid pro quo, that makes things so much easier. Then all we have to deal with is the FCC notification. We don't have to deal with orbital debris. We don't have to deal with, you know, what happens if we poke a hole in somebody else's satellite. It's on them. If we do this more often, like we've done with some of our LTM partners, we can see an up-tempo launch cadence. We could get to that maybe twice a year, maybe more than that. And we can have a continuous stream of low Earth orbit satellites for our users here and worldwide to use. And there's plenty of both commercial and non-commercial hosted opportunities. We've had to pass some by, I'm sorry to say. Once we get the rest of these LTMs and the PACSAT and the other payloads ready to go on the shelf, so we can respond in a quick manner, we'll see more of these hosted payload missions, I hope. MEO, HEO, and GEO. Oh, how I want to be there. Hosted opportunities exist right now. There are companies advertising for hosted payloads to GEO. I will contact them. I will find out how much of that gold we need. I will find out what sort of payloads they are willing to accept. Let's do this. You know, I started out at 16. The day I turned 16, I was sweeping the floors at the local Radio Shack franchise. So I kind of grew up in that, worked there through college, and I learned a lot about sales, although I'm not in sales, I'm a geologist. So my manager used to always say, you have to ask for the sale. Features and benefits, talk the product up, don't let them walk out the door without asking for the sale. We haven't been asking for the sale. We've been waiting for something to float along and come our way and maybe get on board. We have to go out and beat the bushes and look for that sale, for that hosted opportunity. To do this, we need an increased presence at professional conferences. You know, we go to CDW every year. We've been to SmallSat, but not consistently. There are other opportunities out there to get in front of people that can say yes to the sale. Just some crazy ideas. What's an ag cost in space news? Hey, we've got this payload that we'd like to fly somewhere above 550. Can you help us? You know, maybe with a picture of a kid with an arrow just to juice it up a little bit. We need to find out where our industry insiders are in our ranks. We have people in our organization, as a friend of mine once said, or was often said, we need to find the low people in high places. So, you know, if we've got a VP of something for some space organization in our ranks, boy, we'd like to talk to you, maybe butter you up a little bit for that sale. We've got government contacts. The government is launching stuff all the time. Air Force, Space Force, you know, there's all sorts of government satellites in the works. And a lot of them are pretty big and might have a little half kilogram extra capacity. So we need to work that angle as well. To back this up, we have to have something that we can fly, because a lot of these are going to be short notice. We're doing that with the LTM. We're going to do that with PACSAT. We can have other packages with SDRB that are ready to go, maybe a little bit of tweaking to get it to fit the opportunity, but we have to have those. We have to have those ready to go, because when they say, yeah, we're going to do it, we're launching in 6 months, we can't take a year to pull something together. So it has to be some sort of prepackaged, pre-ready stuff. Additionally, you know, all those 3 payloads that I mentioned are all great. I love them all. But they're not gonna fit every opportunity. If we hit the jackpot, if that scratcher comes back with all the same number on it, to GEO or to HEO, what are we gonna put there? So we need to have a conceptual quiver full of missions. Basically, hey, we got a stabilized platform in MEO, maybe we reach back and we pull out a 10 gig downlink. You know, we got something going to GTO, but it's got to be real simple. Maybe we throw a digipeater up there. We have to be thinking about this stuff ahead of time and have the building blocks to put together to make something that'll work. So that's more a thought experiment than actual hardware. You know, let's figure out what we can do on a short time frame. And how many people in here worked GreenCube, IO117? Well, about a quarter. That's a good number. Man, wasn't that something? 6,000 kilometer orbit from Florida. I worked South Africa. I worked Korea. I worked the Ukraine. I worked Sakhalin Island. All on a 1200 baud digipeater that was a secondary mission and a 3U CubeSat that was not rad hard. Was designed for LEO. Not saying they didn't do anything, but there were I think it was four satellites on that launch that had amateur radio payloads, and it was the only one that lasted more than a couple of weeks. So, you know, that's the sort of simple mission that we're talking about. You know, get our toe in the door to get back to a higher orbit. Any reasonable payload in any orbit above LEO is going to be massively popular, and we're going to see those membership ranks swell. Last slide, I promise. This is kind of a catch-all, so I don't have a little subtitle, past opportunities. This is the miscellaneous page. I want to reestablish and strengthen international communications and collaboration. We really took a big hit with ITAR, and frankly, I'm tired of hearing about it. We have ways to work around it. And just because we have some restrictions on ITAR and EAR doesn't mean that we can't talk to our friends in other AMSAT organizations. It doesn't mean that we can't share things via the avenues that we have to get around those hurdles. And I feel that over the past 20 years, or 25 years since ITAR reared its ugly head and tore us apart, that those communications have really suffered. There are other organizations around the world that have hardware ready to go. We should know about that, and they should know about what we have ready to go. And we should work together better. And I think that this is coming around, but I think that AMSAT should lead the way, and there should be regular meetings between other AMSAT organizations, leadership, and us. I really think that's important, and that's a low-hanging fruit. So we're going to snatch that one off right away. We talked in the board meeting about establishing a BOD advisory committee. These are people that have expertise in different subjects that we need, that maybe don't want to get abused on the board full-time or as an officer, but people that we need to be able to reach out to and say, hey, what's your opinion on this? Are we screwing this up? Is there a better way to do this? Is there something we don't know? Or maybe they reach out to us and say, hey, you could do this a little differently. Or, hey, I know a guy. You know, I know a guy has some really important, powerful words. So hopefully we've asked Barry and Mark to head that up. So we hope that that comes to fruition soon. They did a great job on the presidential search after Robert decided to not be president again. And I'm not just saying that because I'm the president now. I'm probably saying that despite the fact I'm the president now. So, and I want to thank all the other candidates that worked through that process. So I've got nothing but the utmost faith in Barry and Mark to pull that forward. And we'll be looking at a new strategic planning meeting within the next 6 months for the board and officers and invited guests and maybe even some of those advisory committee to try to chart a new path forward, make sure we're walking right and headed in the right direction. Not that we haven't been, but this is something we do every 10 years or so. I think maybe every 5 years, just to make sure that we've got everything lined up the way it should be. So that's the last slide. I'm going to take a drink, and any questions, comments? This is the membership meeting. I'm wet behind the ears and weak in the knees, but I'll do the best to answer any questions that you might have. Really?
Any questions? Come on now. This is your opportunity, maybe the last one for at least a year, to put Drew on the hot spot.
Oh, yeah. Boy, I had a big one, and I walked right, 2 things. I walked right past it. It's because it's written on my hand. Yes, exactly, Palm Pilot Mark I. Just a little thing that I want to start, you know, if AMSAT was a newspaper or a magazine or a website developer, we'd have a style guide. I want to correct, because I see quite often people refer to us as AMSAT NA or AMSAT US. We're not. We're AMSAT. We're the mothership. We're the original one. And in particular, AMSAT Canada spun off last year. They are their own organization. So we really can't claim AMSAT NA anymore, even if we wanted to. But when you're writing, we're AMSAT. That's just a little side thing. I expect a little pushback on that, but that's okay. The other thing I wanted to announce, and I briefly talked to Jerry. We talked about this in closed session the other morning. I'm sorry everybody couldn't listen in on it, but when it comes to financial negotiations with outside entities, you just can't do that. I'm happy to say that we are pursuing a 1U launch with a partner, tentatively June of 27. Now, where that fits in, that may be B, that may be A, that may be C, who knows? But it's at a substantial discount, and it's with a partner, and that partner is AMSAT UK. As we were discussing earlier, or Mike was mentioning earlier, a 2U launch costs about the same as a 3U launch because it's really hard to find a 1U partner. A lot of the deployments now are 3U or 6U. So AMSAT UK reached out, offered it to us. The board has not voted on it, but given a sense of the board that it is appropriate to pursue. I think I worded that right. Appropriate to pursue for tentatively a June 27 launch with AMSAT UK's FunCube Plus and the deployer next to us, a 2U satellite. So we're working on it. Any other questions or any questions at all? All right, thank you very much.
Okay, so at 6 o'clock is the attitude adjustment session, the social hour before the banquet. And then that will be hosted, I guess, in Salon A or, oh, right, in this room right here. Okay, right here. And then we're going to have our banquet starting at 7 o'clock. Remember on your name, raffle ticket name, to put your call sign. So when you turn that in, name doesn't win, you do. And then that's it. But it's been a great symposium and annual meeting. I thank all of you for attending. We couldn't have done it without you. So we'll see you tonight. Have fun.